Hey everyone, and welcome back to Scientific Discovery Hub. Have you ever looked up at the night sky and wondered, are we alone? The universe is staggeringly vast, teeming with billions of stars, planets, and the building blocks of life. Yet despite all this potential, there's an eerie silence. No signals, no visitors, no proof of intelligent life beyond Earth. This cosmic mystery is at the heart of one of science's most intriguing puzzles, the Fermi Paradox. In this video, we'll dive into the mind-bending question Enrico Fermi famously posed in 1950. Where is everybody? How can a universe so rich in possibilities hold no trace of alien civilizations? We'll break down the science, theories, and discoveries that shape this debate, from the Drake equation, which tries to calculate the odds of extraterrestrial life, to the chilling Great Filter hypothesis, which suggests a hidden barrier might prevent civilizations from thriving. You'll explore ideas like the rare Earth hypothesis, which argues that planets like ours might be incredibly rare, and learn how exoplanet discoveries are rewriting our understanding of habitability. We'll also tackle cutting-edge concepts like technosignatures. Could we spot alien technology? The dark forest hypothesis, a universe of hidden predators, and even the mind-blowing idea of a multiverse where infinite realities might play out beyond our cosmic horizon. Whether you're a seasoned space enthusiast or new to astrophysics, this video will take you on a journey through the cosmic evolution of life, the limits of astrobiology, and the urgent race to decode the universe's silence. Along the way, we'll ask, is humanity alone? Are we living in a cosmic Goldilocks moment? And what does it all mean for our future among the stars? So hit that play button, grab a snack, and join us as we unravel one of science's greatest enigmas. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the wonders of the universe. The cosmos is waiting, and trust us, you won't want to miss what's out there. Standing beneath the endless expanse of the night sky, one cannot help but feel a profound sense of awe and isolation. The universe stretches in every direction, an infinite ocean of stars, galaxies, and celestial phenomena, each holding the potential for worlds beyond our imagining. Yet, despite this staggering scale and age, the cosmos remains eerily silent. No signals, no artifacts, no unmistakable signs of other intelligent beings have been detected. It is as if we are the only voice in an otherwise empty cathedral of space. This paradox, the expectation that intelligent life must be abundant, yet the complete absence of any confirmed evidence, has haunted scientists and thinkers for decades. At the heart of this enigma lies a seemingly simple question, first posed by physicist Enrico Fermi during a casual lunchtime conversation in 1950. As he looked out over the rooftops of Los Alamos, Fermi mused, "Where is everybody?" His words were deceptively brief, yet they struck at the core of a deep and unsettling truth. Given the sheer number of stars and planets in the universe, the probability of life emerging elsewhere should be astronomically high, and yet not a single trace of such life has been found. This contradiction between expectation and observation forms the foundation of what is now known as the Fermi Paradox. The paradox does not merely challenge our understanding of the universe, it compels us to reconsider fundamental assumptions about life, intelligence, and the nature of existence itself. If the universe is as vast and ancient as we believe, then it seems logical that life should have arisen many times across the cosmos. The conditions necessary for life, liquid water, organic molecules, and stable planetary environments are not unique to Earth. These elements are scattered throughout the galaxy, embedded in the very fabric of the cosmos. So why, after billions of years of cosmic evolution, has no one else reached out to us? Is it possible that we are truly alone? Or perhaps there is something we have yet to understand about the nature of life, intelligence, and the universe's hidden rules? Fermi's question lingers like a riddle, a whisper from the void that refuses to be answered. It is a reminder that the universe is not only vast in space and time, but also in mystery. The Fermi Paradox invites us to explore the limits of our knowledge, to probe the boundaries of possibility, and to contemplate our place within the grand design of the cosmos. The Fermi Paradox, arises from a fundamental contradiction between statistical probability and observed reality. Given the sheer scale of the universe, the likelihood of intelligent life existing elsewhere seems almost inevitable. Astronomers estimate that there are at least 100 billion galaxies in the observable universe, each containing hundreds of billions of stars. Around many of these stars orbit planets, some of which lie within the so-called habitable zone, the region where liquid water could exist on a planet's surface. Recent discoveries have revealed that such potentially habitable worlds may be more common than once believed. Exoplanets with Earth-like characteristics have been identified in distant star systems, some even possessing atmospheres that could support life. With such an abundance of suitable environments, the odds appear overwhelmingly in favor of life having emerged multiple times across the cosmos. Yet, despite these favorable conditions, no definitive evidence of extraterrestrial intelligence has ever been discovered. The absence of signals, artifacts, or any other indicators of advanced civilizations raises a profound question. If intelligent life is so likely to arise, why do we remain the sole known example? This conundrum is compounded by the vast age of the universe. At nearly 13.8 billion years old, it has had ample time for intelligent species to develop, expand, and perhaps even colonize other star systems. If even a small fraction of those civilizations manage to achieve interstellar travel, their influence should be detectable by now. The fact that we see no such evidence suggests either that intelligent life is far rarer than expected, or that there exists some fundamental barrier preventing civilizations from making themselves known. This paradox is further amplified by the Drake equation, a mathematical framework devised by astrophysicist Frank Drake in 1961 to estimate the number of detectable civilizations in the Milky Way galaxy. The equation considers several critical variables, including the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the likelihood of life developing on those planets, and the probability of that life evolving into intelligent, technologically advanced societies. While the values used in the equation remain highly speculative, even conservative estimates suggest that there should be at least a few detectable civilizations within our galaxy. However, the complete absence of any confirmed signals or artifacts challenges the assumptions underlying the equation, forcing scientists to reconsider whether their models accurately reflect reality. The Fermi Paradox is not merely a problem of numbers, it is a reflection of our incomplete understanding of the universe. It forces us to confront the possibility that our current models of life's origins, the evolution of intelligence, and the nature of cosmic civilizations may be fundamentally flawed. Perhaps the emergence of life is an exceedingly rare event, constrained by factors we have yet to identify. Alternatively, maybe intelligent civilizations, when they do arise, tend to self-destruct before they can make their presence known. Or perhaps there is another, more profound reason why the universe remains silent. Whatever the case may be, the Fermi Paradox serves as a humbling reminder of the vastness of the unknown and the limitations of human knowledge. The Fermi Paradox compels us to consider a spectrum of possibilities, each revealing a different facet of the universe's enigmatic nature. One approach to resolving the paradox is the rare Earth hypothesis, which posits that while life-sustaining planets may be relatively common, the specific combination of conditions required for complex intelligent life is extraordinarily rare. Earth's history is marked by a series of fortuitous events, such as the presence of a large moon stabilizing its axial tilt, plate tectonics recycling atmospheric gases, and the absence of frequent asteroid impacts that have allowed life to flourish and evolve without catastrophic interruption. If such circumstances are uncommon in the universe, then the emergence of intelligent civilizations may be a statistical anomaly rather than an inevitability. This perspective shifts the focus from the sheer number of potentially habitable planets to the intricate web of factors that govern the development of life as we know it. Another compelling explanation lies in the Great Filter hypothesis, which suggests that there exists a critical threshold in the evolutionary journey from simple life to an advanced spacefaring civilization. This filter could act as a universal bottleneck, preventing most species from progressing beyond a certain stage. If the Great Filter is behind us, meaning that the emergence of intelligent life is exceedingly difficult, then Earth's position as a rare outlier gains new significance. However, if the Great Filter lies ahead, it implies a sobering truth. Advanced civilizations may frequently reach a point where they are unable to transcend self-destruction, whether through environmental collapse, resource depletion, or technological catastrophe. This scenario raises profound questions about humanity's trajectory. Are we already on a path toward annihilation, or do we stand at a crossroads where our survival hinges on choices yet to be made? The Great Filter hypothesis thus reframes the paradox, not as a question of existence but as a warning about the fragility of progress. The zoo hypothesis offers a more speculative but equally thought-provoking angle. It proposes that advanced civilizations may be aware of our existence but have chosen to remain hidden, treating Earth as a protected reserve in a cosmic zoo. According to this idea, extraterrestrials might adhere to a strict policy of non-interference, allowing humanity to evolve independently without external influence. Such a scenario would align with ethical considerations akin to those faced by conservationists on Earth, who strive to preserve ecosystems without disrupting their natural processes. If true, the zoo hypothesis suggests that our isolation is not due to the absence of others, but rather to deliberate restraint. Yet this explanation also raises unsettling questions. What criteria determine which civilizations deserve to be left undisturbed? Could our actions, however unintentional, breach the boundaries of this cosmic quarantine? On the other hand, the dark forest hypothesis, popularized in science fiction and rooted in strategic game theory, presents a darker interpretation. It posits that the universe is a battleground where civilizations, driven by survival instincts, conceal themselves to avoid detection by hostile neighbors. In this grim vision, the act of revealing one's existence could invite annihilation, leading to a universal imperative of silence. This theory underscores the potential for interspecies conflict to dominate the cosmos, with civilizations prioritizing preemptive strikes over peaceful coexistence. If the dark forest hypothesis holds, then the Fermi Paradox is less a mystery and more a testament to the ruthless efficiency of cosmic competition. Such a perspective challenges humanity to consider the moral implications of our own expansion into space. Would we risk exposing ourselves to an indifferent or malevolent universe? Or would we adopt strategies of stealth and caution to ensure our survival? These possibilities, though diverse, share a common thread. They compel us to re-evaluate our assumptions about the universe and our place within it. The Fermi Paradox is not merely a puzzle to be solved, but a mirror reflecting our deepest uncertainties. It forces us to confront the possibility that the cosmos may be either a lonely expanse or a theater of unseen forces operating according to rules we have yet to comprehend. Whether the answer lies in the rarity of life, the inevitability of self-destruction, or the deliberate concealment of others, the paradox serves as a humbling reminder of the vastness of the unknown. It challenges us to look beyond our immediate concerns and to consider the broader implications of our existence, not as isolated beings, but as participants in a story whose full dimensions remain obscured by the darkness of space. To begin unraveling the Fermi Paradox, scientists have turned to a powerful conceptual tool, the Drake equation, formulated in 1961 by radio astronomer Frank Drake. This equation provides a structured way to estimate the number of active communicative extraterrestrial civilizations in the Milky Way galaxy. At its core, the Drake equation is not a definitive calculation, but a framework, a means of organizing the many unknowns that shape our understanding of the universe's potential for life. By breaking down the problem into quantifiable components, the equation allows researchers to test hypotheses, refine assumptions, and guide future exploration. Its simplicity belies its profound implications, as each variable represents a critical threshold in the development of intelligent life. The equation begins with the rate of star formation in the galaxy, a value that reflects how quickly new stars are born. This number sets the foundation for the rest of the equation, as each star represents a potential cradle for planetary systems. From there, the next step is to estimate the fraction of those stars that host planets, a factor that was once speculative but has been dramatically clarified by modern astronomy. Observations from missions like NASA's Kepler Space Telescope have shown that planets are not rare anomalies, but rather the rule. With nearly every star in the galaxy likely accompanied by at least one orbiting world, the next variable considers the number of planets per system that lie within the habitable zone, the region where conditions may allow for liquid water, a key ingredient for life as we know it. While the habitable zone is not a guarantee of life, it represents a crucial starting point. Some systems may host multiple habitable planets, while others may have none at all. Even among those within the right distance from their star, additional factors such as atmospheric composition, geological activity, and magnetic fields play a role in determining whether life can take hold. Beyond habitability, the equation explores the likelihood of life actually arising on a suitable planet. This is one of the most uncertain factors, as it depends on the mysterious process of abiogenesis, the transition from inorganic matter to self-replicating molecules capable of evolution. While we know the building blocks of life exist throughout the cosmos, we still do not fully understand how life first emerged on Earth, let alone how likely such a process is to occur elsewhere. If life is common, then the next steps in the equation become even more significant. The probability that life evolves into intelligent, technologically advanced beings, and the duration for which such civilizations remain detectable. Each of these variables introduces layers of complexity, and collectively, they illustrate the vast uncertainties surrounding the existence of extraterrestrial civilizations. While the Drake equation is often cited as a means of estimating the number of intelligent species in the galaxy, it is, in reality, a tool for framing the unknown. It reminds us that the Fermi Paradox is not just a question of numbers, but a reflection of our limited understanding of life's origins, the evolution of intelligence, and the long-term survival of civilizations. As we continue to explore the cosmos, the Drake equation will remain a guiding light, a way to navigate the vast and uncharted territory of the universe. Beneath the velvet tapestry of the night sky, where constellations shimmer like ancient hieroglyphs, humanity has long gazed upward, seeking answers to its most profound questions. What lies beyond the veil of stars? Are we alone in this boundless expanse? These inquiries, etched into the marrow of human curiosity, took a pivotal turn in 1961 when astronomer Frank Drake devised a mathematical framework to quantify the immeasurable. The Drake equation, born from the crucible of post-Sputnik optimism and Cold War-era scientific ambition, transformed the abstract into the tangible. It offered a roadmap not for certainty, but for inquiry, a lens through which to peer into the cosmic unknown. At its heart lies a paradox. The universe, so vast and indifferent, becomes a stage for our fragile, flickering hopes of connection. Drake's equation emerged during a confluence of intellectual currents. The dawn of radio astronomy had unveiled the electromagnetic whispers of distant stars, while the discovery of organic molecules in interstellar clouds hinted at chemistry's universality. The space age had ignited imaginations, and the search for extraterrestrial intelligence, SETI, was taking shape as both a scientific endeavor and a philosophical odyssey. Yet, the equation itself was never intended to yield definitive numbers. Instead, it sought to frame the questions that would define generations of scientists. What is the probability that life arises from the primordial soup? How often does intelligence emerge from evolutionary chaos? These were not mere academic exercises, they were invitations to confront the scale of our ignorance and the audacity of our dreams. To grasp the significance of the Drake equation is to embrace the humility of uncertainty. Each term within its elegant structure, a product of 7 variables, represents a frontier of knowledge, a boundary between what we know and what we do not. It is a testament to the human spirit, which dares to measure the immeasurable and to find meaning in the void. As we delve into its components, we are reminded that the cosmos is not merely a backdrop for our existence. The equation, in its simplicity and complexity, mirrors the universe itself, infinite in possibility, finite in our grasp. At its core, the Drake equation is a multiplication of probabilities, each variable a stepping stone toward estimating the number of detectable civilizations in the Milky Way. The first term, R-share, the rate of star formation, anchors the equation in the observable. Current astrophysical models, suggest that the Milky Way births approximately 1 to 3 new stars annually, a slow but steady rhythm of creation. Yet this number, once thought static, has evolved with advancements in observational techniques. Infrared surveys reveal hidden nurseries of star formation, while gamma-ray bursts challenge our understanding of stellar life cycles. The universe, it seems, is far more dynamic than early 20th century cosmology imagined. The second variable, the clash, the fraction of stars with planets, once existed in the realm of speculation. Before the 1990s, planetary systems beyond our own were theoretical constructs. Then came the Kepler Space Telescope, a robotic sentinel that revolutionized our view of the cosmos. Its data revealed that nearly every star hosts planets, some orbiting in tight, scorching orbits, others drifting in frozen isolation. The realization that planets are common, a cosmic norm rather than an anomaly, shifted the equation's foundation. Yet the presence of planets alone is insufficient. What matters is whether they lie within the Goldilocks zone, where temperatures permit liquid water. This leads to the third term, NOD, the number of habitable planets per system, a metric still shrouded in ambiguity. While some systems host multiple potentially habitable worlds, others may harbor none. The diversity of exoplanets from super-Earths to mini-Neptunes underscores the need for nuance. A planet's size, atmospheric composition, and geological activity all influence its habitability, factors that remain beyond our current reach to measure en masse. The fourth variable, F-arc, the likelihood of life emerging, plunges us into the domain of abiogenesis, the alchemy by which non-living matter gives rise to living organisms. On Earth, life appeared remarkably quickly after the planet cooled, suggesting that the conditions for its origin may be widespread. However, the precise mechanisms remain elusive. Laboratory experiments have synthesized amino acids under simulated primordial conditions, yet the leap from molecular building blocks to self-replicating systems remains unexplained. The discovery of extremophiles, organisms thriving in hydrothermal vents, acidic lakes, and subglacial oceans, expands our definition of habitability, implying that life may flourish in environments once deemed inhospitable. If life arises readily, as these findings suggest, the universe teems with microbial ecosystems, unseen but present. The fifth term, Finite, the chance of intelligence arising, introduces a quantum leap in complexity. Evolution is a tangle of contingency and constraint, shaped by environmental pressures and genetic accidents. On Earth, intelligence emerged only once among the vast tree of life. Yet this may be a statistical artifact rather than a universal rule. Consider the octopus, a cephalopod with advanced problem-solving skills and no backbone, or the social intricacies of ants and bees. Intelligence, in its myriad forms, may be more common than we assume. Still, the path from single-celled organisms to sentient beings is fraught with unknowns. Did the Cambrian explosion, which birthed complex multicellular life, represent a necessary phase in evolution? Or was it a cosmic fluke? Such questions linger unanswered, their resolution dependent on the study of exoplanetary biospheres, research now enabled by spectroscopic analysis of atmospheric biosignatures. The sixth variable, Fanon mass, the development of technology, hinges on a civilization's ability to harness energy and communicate across interstellar distances. Human history offers a fleeting glimpse into this trajectory, from fire to electricity, from smoke signals to radio waves. Yet the timescale for such progress is minuscule compared to the age of the universe. If a species evolves intelligence but lacks the resources or stability to develop technology, it may fade into obscurity. Conversely, rapid technological advancement could lead to self-destruction, a cautionary tale for our own civilization. The equation's final term, L, the lifespan of detectable civilizations, encapsulates this existential gamble. Is our era of radio emissions and optical telescopes a brief blip in the cosmic timeline, or will we endure long enough to become a beacon in the dark? The answer may depend on factors as varied as climate change, nuclear deterrence, and the ethical stewardship of artificial intelligence. Together, these 7 variables form a mosaic of possibilities, each term a mirror reflecting our deepest uncertainties. The Drake equation is not a prophecy, but a provocation, a call to refine our knowledge and broaden our horizons. As we move from the theoretical to the practical, we must grapple with the implications of these numbers, not just for science, but for philosophy, ethics, and our collective future. When the Drake equation is applied with conservative estimates, the results are humbling. Suppose we adopt the lowest plausible values, a star formation rate of 1 per year, 50% of stars hosting planets, 1 habitable planet per system, and 1% probabilities for life, intelligence, and technological development. Even if a civilization lasts a mere 10,000 years before vanishing, a blink in cosmic terms, this yields approximately 10 detectable civilizations in the Milky Way. Multiply that by the galaxy's 4.5 billion year history, and the number swells to thousands. Yet these figures are arbitrary, their validity contingent on assumptions that may soon shift with new discoveries. Consider the role of astrobiology in refining FET. Recent studies of Martian meteorites and Europa's subsurface ocean suggest that life may not require Earth-like conditions. If extremophiles thrive in the icy crusts of moons or the volcanic plumes of Enceladus, the threshold for habitability widens. Similarly, advances in synthetic biology challenge our anthropocentric definitions of life. Could silicon-based organisms or self-replicating nanomachines exist elsewhere? Such possibilities, once dismissed as science fiction, now demand serious consideration. Each breakthrough in understanding life's adaptability rewrites the parameters of the equation, pushing the lower bounds of F higher. The variable F, however, remains the most contentious. Evolution on Earth followed a singular path, but this may not be representative of the universe at large. The fossil record reveals repeated mass extinctions, each reshaping the course of biological innovation. If intelligence is a rare emergent property, perhaps constrained by the need for complex brains and social structures, then F dwindles. Conversely, if intelligence arises as an inevitable outcome of natural selection, akin to photosynthesis or sexual reproduction, then F approaches 1. The discovery of exoplanets with diverse geologies and atmospheres may one day resolve this debate, but for now it remains a philosophical chasm. The term F further complicates the equation. Technological development is not guaranteed. It requires stable environments, abundant resources, and cultural continuity. Civilizations that arise in star systems, devoid of heavy elements necessary for building advanced tools, may stagnate at a pre-industrial level. Others may face existential threats from asteroid impacts, supernovae, or gamma-ray bursts. The James Webb Space Telescope, with its ability to analyze the chemical composition of exoplanetary atmospheres, could soon identify signs of industrial pollution or artificial satellites. Such detections would not only validate the equation's framework, but also redefine our understanding of civilization building. Yet even the most optimistic scenarios underscore the fragility of detectable civilizations. The variable L, representing a civilization's lifespan, is perhaps the most speculative. Human history provides a grim precedent. Empires rise and fall within centuries, their legacies buried beneath sand and silence. If our species endures another millennium, we may yet become a galactic signal. But if climate collapse, nuclear war, or ecological degradation shortens our tenure, the universe will remain deaf to our existence. The equation thus serves as both a mirror and a warning, reflecting our hubris and vulnerability. The Drake equation's true power lies in its capacity to evolve. As we unravel the mysteries of dark matter, quantum gravity, and the origins of the universe, the variables shift. The discovery of a second genesis of life on Titan or Venus would recalibrate FEC, while the detection of alien artifacts in the Oort cloud would render L irrelevant. In this light, the equation is not a static formula, but a living dialogue between science and speculation. It challenges us to confront the limits of our knowledge while inspiring the pursuit of answers. If the Drake equation suggests a universe teeming with civilizations, why do we hear only the echo of our own radio waves? This paradox, known as the Fermi Paradox, looms over every calculation. The silence of the cosmos is deafening, a void that resists easy explanation. One theory, the Great Filter, posits that a critical barrier, biological, societal, or cosmic prevents life from advancing to the interstellar stage? Is this filter behind us, ensuring that intelligent life is exceedingly rare? Or is it ahead, a looming catastrophe that awaits all who dare to ascend? The Great Filter hypothesis invites us to examine the trajectory of life on Earth. Did the emergence of eukaryotic cells or the development of oxygen-rich atmospheres represent insurmountable hurdles? Or perhaps the bottleneck lies in the transition from tool use to interplanetary travel, a chasm that few civilizations may cross. The answer, if it exists, may lie in the study of our own vulnerability. Climate change, biodiversity loss, and the proliferation of artificial intelligence all mirror the existential risks that could truncate a civilization's lifespan. As we pivot from the Drake equation to the Great Filter, we enter a realm of darker possibilities. The equation's variables, once symbols of hope, now cast long shadows. The next segment will explore this cosmic threshold, the unseen force that may determine whether we are destined to join the chorus of the universe or remain a solitary note in its symphony. In the vast, glittering tapestry of the universe, where galaxies spiral like celestial dancers and stars are born from the remnants of ancient explosions, a profound question lingers unanswered. Where is everyone? The cosmos teems with planets, many of which orbit within the habitable zones of their stars, their surfaces potentially cradling oceans and atmospheres. Yet, despite the staggering number of such worlds, not a single signal, artifact, or sign of intelligent life has been detected beyond Earth. This paradox, the Fermi Paradox, has haunted scientists, philosophers, and dreamers for decades. What could account for the eerie stillness of the galaxy? The answer, some argue, lies in a single enigmatic concept: the Great Filter, a bottleneck, a wall of fire or ice, a chasm carved into the timeline of life's evolution, separating the raw potential of existence from the reality of interstellar empires. Somewhere between the first self-replicating molecules in Earth's primordial soup and the hypothetical civilizations harnessing the energy of entire star systems, a threshold exists, and whether it has already shaped our fate or looms ahead as a shadowy specter remains one of the most haunting mysteries of our age. To imagine the Great Filter is to peer into the abyss of possibility. It is not a single event, but a collection of improbable steps, each a potential roadblock in the journey from life's inception to its ultimate triumph across the stars. Could it be that the leap from simple cells to complex organisms is so astronomically rare that only a handful of planets in the observable universe ever achieve it? Or perhaps, despite reaching the heights of technology, civilizations repeatedly unravel under the weight of their own ambition, their light extinguished before it can touch the void. The Great Filter is not merely a scientific puzzle. It is a mirror held up to humanity, reflecting our deepest fears and highest hopes. Are we alone because we are exceptional, or because we are doomed? The Great Filter, first articulated by economist Robin Hanson in 1996, is a theoretical explanation for the Fermi Paradox. At its core, the concept posits that at least one step in the sequence of events leading to a technologically advanced civilization is exceptionally unlikely. These steps span billions of years and encompass a spectrum of biological, geological, and socio-political challenges. To grasp the enormity of the filter, consider the evolutionary odyssey that brought life on Earth to its present state. The first hurdle may be the origin of life itself, the transition from inert chemistry to self-replicating molecules capable of natural selection. On Earth, this process occurred approximately 4 billion years ago, likely in hydrothermal vents or shallow tidal pools, where organic compounds coalesced under the right conditions. Yet, even with the abundance of carbon, water, and energy sources in the universe, the precise combination required to spark life remains elusive. Laboratory experiments have produced amino acids and nucleotides, but the leap to a functional protocell remains a chasm of uncertainty. If this step is common, the universe might be teeming with microbial life, but if it is rare, then life's emergence becomes an extraordinary accident, a cosmic lottery won by Earth alone, or nearly so. Even assuming life arises, the next barrier is the transition to complexity. For nearly 3 billion years after the appearance of the first prokaryotic cells, Earth remained a world of single-celled organisms. The evolution of eukaryotic cells, those with nuclei and organelles, required a symbiotic fusion of species, a partnership so radical it redefined life itself. This innovation enabled multicellularity, allowing organisms to specialize and diversify into the vast array of plants, animals and fungi that now dominate ecosystems. Yet this step was not inevitable. Fossil records suggest that multicellular life emerged independently multiple times on Earth, but only once did it lead to the explosive Cambrian explosion of biodiversity. Other lineages, like the Ediacarans, faded without leaving descendants. If the path to complexity is fraught with dead ends, then even planets with life may remain stagnant in simplicity. Beyond biology, the great filter could reside in the development of intelligence. While intelligence is often seen as the pinnacle of evolution, it is not universally favored by natural selection. Many species thrive without it, relying on instinct and adaptation. The rise of Homo sapiens, with its capacity for abstract thought, tool-making, and language, was a product of unique environmental pressures and genetic serendipity. Even if other planets host intelligent species, they may lack the cultural or cognitive traits necessary to pursue science. Moreover, intelligence does not guarantee survival. The dinosaurs, despite their dominance for 160 million years, were undone by an asteroid strike, a reminder that even well-adapted species are vulnerable to cosmic randomness. Yet perhaps the most chilling possibility is that the great filter lies ahead of us. Here, the focus shifts from the past to the future, from evolutionary inevitabilities to human-made crises. Civilizations that reach the technological threshold of interplanetary travel may face existential risks unique to their own progress. Nuclear war, runaway climate change, biotechnological catastrophes, or the unintended consequences of artificial intelligence could all serve as self-inflicted barriers. Consider Earth's trajectory. In just a century, humanity has harnessed nuclear power, altered the climate, and created algorithms that rival human cognition. The same technologies that enable space colonization could also spell our demise. If this is the case, the Great Filter is not a distant natural obstacle, but an intimate, almost philosophical challenge, whether a species can transcend its destructive impulses long enough to become a galactic citizen. Each of these steps represents a potential choke point, a point at which the odds of success plummet. The cumulative effect is staggering. Even if each stage has a 1% chance of occurring, the probability of a civilization reaching interstellar capability would be 10^12, or 1 in a trillion, given the estimated 1022 stars in the observable universe. This would mean roughly 10 civilizations, yet we see none. Such numbers defy intuition, suggesting that either our assumptions are wrong or the filter is impossibly stringent. The implications are profound. If the filter is behind us, then humanity has already navigated the most perilous stages of evolution, making us among the rarest of rare. If it lies ahead, then our survival is a precarious gamble, dependent on choices we have yet to make. The Great Filter forces us to confront a disquieting truth. Our existence may be a statistical outlier, a fluke in the cosmic lottery. If the filter is behind us, then the steps from life's origin to a spacefaring civilization are so improbable that we are effectively the only ones in our galaxy, or perhaps even the observable universe. This scenario, known as the rare Earth interpretation, transforms our perception of ourselves. No longer are we merely inhabitants of a remote planet. We are custodians of a singular achievement, a species that has overcome countless odds to stand at the precipice of interstellar exploration. Such a realization carries immense weight. It imbues our actions with a sense of responsibility, for we are not just shaping our own destiny, but the legacy of life itself. Every decision, whether to preserve biodiversity, mitigate climate change, or develop sustainable technologies, becomes a vote in the ongoing experiment of existence. Conversely, if the Great Filter lies ahead, the stakes are even higher. In this scenario, the future is not a promise, but a precarious balancing act. The very tools that have propelled humanity forward, nuclear energy, artificial intelligence, genetic engineering, could also be the instruments of our undoing. Consider the specter of nuclear annihilation. For over half a century, the world has lived under the threat of mutually assured destruction. a fragile peace sustained by deterrence and diplomacy. Climate change adds another layer of urgency, as rising temperatures, extreme weather, and resource scarcity strain the delicate equilibrium of our biosphere. Meanwhile, the rapid advancement of artificial intelligence raises existential questions about control, ethics, and the potential for unintended consequences. A superintelligent AI, if misaligned with human values, could optimize the world in ways catastrophic to our survival. These risks are not abstract, they are immediate, demanding foresight and cooperation on a scale never before attempted. The duality of the Great Filter, its potential location in the past or future, frames our present as a crossroads. If we have already passed the most dangerous stage, we must safeguard the conditions that allowed us to thrive, ensuring that Earth remains a cradle for life's continued evolution. This requires a shift in perspective, from viewing the planet as a resource to be exploited to recognizing it as a complex, interconnected system whose stability is paramount. Conservation efforts, renewable energy transitions, and sustainable agriculture are not just pragmatic choices, but acts of cosmic stewardship. Conversely, if the filter is ahead, we must confront the possibility that our survival hinges on navigating the next few centuries with unprecedented vigilance. This demands global governance structures capable of addressing transnational threats, investment in research to anticipate and mitigate risks, and a cultural shift toward long-term thinking. The Great Filter, in this context, becomes a call to action, a reminder that our species' future is not preordained but shaped by the choices we make today. Yet, the implications extend beyond practical considerations. Philosophically, the Great Filter compels us to grapple with our place in the cosmos. Are we destined to be pioneers, forging paths among the stars? Or are we ephemeral, a brief flicker in the darkness before the flame dies out? This question resonates deeply, echoing the existential inquiries of poets, mystics, and scientists alike. The knowledge that we might be the only conscious beings in the galaxy can inspire both humility and hubris. Humility in recognizing the fragility of our existence, the luck that has brought us this far. Hubris in believing we can overcome any challenge through ingenuity and perseverance. It is a paradox that defines the human condition, to seek meaning in a universe that may offer none, to strive for immortality in a cosmos where time is the ultimate eraser. Moreover, the Great Filter invites reflection on the nature of progress itself. Is the trajectory from primitive societies to spacefaring civilizations an inherent direction of evolution? Or is it a contingent path, one of many possible outcomes? The history of Earth suggests contingency. Dinosaurs, for instance, dominated for millions of years without developing technology, while humans, though intelligent, are not the only species to exhibit complex social behaviors. The rise of Homo sapiens was not a foregone conclusion, but a product of ecological opportunity, genetic drift, and cultural innovation. If other planets followed different evolutionary arcs, their species may have reached entirely different peaks of development, their achievements unrecognizable to us. This possibility challenges anthropocentric views of intelligence and progress, urging us to broaden our definitions of what constitutes a successful civilization. Ultimately, the Great Filter serves as a lens through which to examine both our vulnerabilities and our potential. It underscores the importance of resilience, adaptability, and ethical foresight in the face of uncertainty. Whether we are rare survivors or approaching a perilous threshold, the message is clear: the future is not guaranteed. It must be earned through choices that honor the complexity of life and the vastness of the cosmos. As we ponder the Great Filter, a deeper question emerges. Why is Earth the only planet we know to harbor life? The rare Earth hypothesis offers a provocative answer, suggesting that the conditions necessary for complex life are so improbable that Earth may be an anomaly rather than a template. Unlike the Drake equation, which assumes that life is common once certain conditions are met, the rare Earth hypothesis emphasizes the convergence of rare geological, astronomical, and chemical factors that make our planet hospitable. These include a stable orbit within the habitable zone of a sun-like star, the presence of a large moon to stabilize axial tilt, plate tectonics to regulate climate, and a magnetic field to shield against solar radiation. Add to this the timing of asteroid impacts, cataclysmic events that both delivered essential materials and periodically reset evolutionary trajectories, and the picture becomes even more intricate. This hypothesis reframes the Great Filter by suggesting that the rarity of life itself may be the primary obstacle. If Earth's combination of features is unique, then the emergence of even simple life could be exceedingly uncommon, let alone the subsequent steps to intelligence. This perspective aligns with observations of exoplanets, many of which appear inhospitable due to extreme temperatures, volatile atmospheres, or proximity to unstable stars. While the discovery of extremophiles on Earth has expanded our understanding of where life might exist, it does not negate the possibility that the broader conditions for complex life are extraordinarily rare. The rare Earth hypothesis thus bridges the gap between the Great Filter and the search for extraterrestrial life. It challenges us to look beyond the mere presence of liquid water and consider the full suite of factors that make a planet just right for life's flourishing. As we turn our gaze to the next segment, we must ask, is Earth's uniqueness a fluke, or is it a signpost pointing toward a deeper, universal principle? The answer may lie in the stars themselves, waiting to be deciphered. From the vantage point of a distant spacecraft drifting through the void, Earth appears as a fragile blue marble suspended in the blackness, a single pixel of light in an ocean of stars. This pale blue dot, as Carl Sagan once called it, is the only known cradle of life in the observable universe. Yet beneath its serene surface lies a symphony of interwoven conditions so precise and improbable that they defy casual explanation. Earth orbits its star at a distance that permits liquid water, possesses a magnetic field that shields it from solar radiation, and is accompanied by a massive moon that stabilizes its axial tilt. Its geology is animated by plate tectonics, a process that recycles carbon and regulates climate over eons. These traits, individually and collectively, form a delicate balance that has nurtured the emergence of complex life. But how extraordinary are these circumstances? Are they the product of a cosmic lottery, or do they hint at a deeper order in the universe? The rare Earth hypothesis suggests the former, that the convergence of such conditions is so rare that Earth may be an anomaly in the vast tapestry of galaxies. This idea challenges us to reconsider our place in the cosmos, not as denizens of an average world, but as inhabitants of a singularly improbable haven. To grasp the full weight of this hypothesis, one must first appreciate the staggering scale of the universe. The Milky Way alone hosts an estimated 100 billion stars, each potentially orbited by planets. Beyond our galaxy lie billions more, stretching across the observable universe in an unbroken web of light. Within this immensity, the conditions required for life as we know it appear vanishingly rare. Earth's orbit, for instance, is nestled within the narrow habitable zone of the Sun, where temperatures allow water to remain liquid. Too close, and the oceans would evaporate. Too far, and they would freeze. Even within this zone, Earth's position is not static. Gravitational interactions with other planets and stars could disrupt its orbit over millennia. Yet Earth has remained remarkably stable for billions of years. This stability is no accident. It is the result of a gravitational harmony among the planets and the Sun, a dance of forces that has kept Earth in a safe orbit long enough for life to evolve. But orbital stability is only one piece of the puzzle. Earth's internal dynamics are equally critical. Plate tectonics, the slow but relentless movement of the planet's crust, plays a pivotal role in regulating its climate by recycling carbon dioxide and releasing greenhouse gases. This process maintains a balance that prevents runaway heating or freezing. Without plate tectonics, Earth's atmosphere might resemble that of Venus, a scorching hothouse, or Mars, a barren wasteland. The presence of a large moon further complicates this equation. The moon's gravitational pull stabilizes Earth's axial tilt, preventing chaotic shifts in climate that could render the planet inhospitable to life. Imagine a world where seasons fluctuate wildly, where ice ages and tropical epochs collide in unpredictable cycles. Such a world, though theoretically possible, would struggle to sustain the biodiversity that defines Earth. These conditions, however, are not self-sufficient. They depend on a chain of fortuitous events stretching back to the birth of the solar system. Earth's magnetic field, generated by the churning of molten iron in its core, protects the planet from the sun's deadly solar wind. Without this shield, atmospheric particles would be stripped away, leaving the surface exposed to radiation. The magnetic field itself is a product of Earth's size and composition too small, and the core would cool too quickly, too large, and the planet's gravity would crush life under its own weight. Even the chemical makeup of Earth's crust and oceans is finely tuned. The abundance of oxygen, the presence of carbon-based molecules, and the availability of essential elements, like phosphorus and sulfur, are all prerequisites for the biochemical processes that sustain life. Each of these factors seems to conspire in a way that borders on the miraculous. The rare Earth hypothesis posits that such a confluence of conditions is exceedingly rare. While microbial life might thrive on other worlds, perhaps in the subsurface oceans of Europa or the methane lakes of Titan, planets capable of hosting intelligent life may be outliers in the cosmic census. This raises a profound question. Is Earth a fluke, a statistical aberration in a universe teeming with potential, or is it a necessary outcome of natural laws we have yet to fully comprehend? As we delve deeper into the mechanics of the hypothesis, we uncover a narrative that intertwines astrophysics, geology, and biology into a single intricate story of cosmic improbability. At the heart of the rare Earth hypothesis lies a recognition of the galaxy's uneven distribution of life-friendly environments. The Milky Way, though vast, is not uniformly hospitable. Its spiral arms, dense with gas and dust, are regions of active star formation, but also prone to violent supernovae and gamma-ray bursts. These cataclysmic events can sterilize entire star systems, erasing any nascent life before it has a chance to develop. In contrast, the galactic habitable zone, a ring-shaped region between the galactic's center and its outer edges, offers a more tranquil refuge. Here, the density of stars is lower, reducing the risk of disruptive collisions, while the concentration of heavier elements is sufficient to form terrestrial planets. However, even within this zone, the odds of finding a planet with Earth-like conditions are minuscule. Stars must be of the right type, neither too massive nor too dim. Massive stars burn out quickly, leaving little time for life to evolve, while red dwarfs emit intense flares that could strip atmospheres. Our Sun, a G-type main sequence star, occupies a sweet spot in this stellar hierarchy, providing steady energy over billions of years. Beyond stellar properties, the architecture of a planetary system plays a critical role. The presence of a gas giant like Jupiter acts as a gravitational sentinel, deflecting comets and asteroids that might otherwise collide with inner planets. Computer simulations suggest that without such a guardian, Earth would endure a barrage of impacts far more frequent than the relatively calm history we observe. Jupiter's immense mass, combined with its distant orbit, creates a protective buffer that shields the inner solar system from debris, yet this arrangement is precarious. If Jupiter were closer, its gravity could destabilize Earth's orbit. If smaller, it would lack the clout to clear the asteroid belt. The delicate balance of our solar system's design hints at a series of coincidences that defy easy replication elsewhere. Even assuming a star of the right type and a protective gas giant, the planet itself must meet stringent criteria. Size matters profoundly. A planet too small cannot retain an atmosphere, while one too large becomes a hostile super-Earth, with crushing gravity and volcanic activity. Earth's mass allows it to hold onto volatile compounds like water and nitrogen, while remaining hospitable to life. Its composition is equally vital. A planet rich in silicates and metals can generate a magnetic field, whereas one dominated by hydrogen and helium would lack the geological activity necessary for recycling carbon and sustaining climate stability. The chemical diversity of Earth derived from the debris of ancient supernovae is a prerequisite for the complex biochemistry of life. Every atom in our bodies, from the calcium in our bones to the iron in our blood, was forged in the hearts of dying stars, scattered across the cosmos, and assembled into a world uniquely suited for life. The rare Earth hypothesis does not merely catalogue these conditions, it underscores their interdependence. A planet with a suitable star and orbit is still doomed if it lacks plate tectonics or a magnetic field. A world with abundant water and a temperate climate is wasted if it cannot regulate its temperature over geological timescales. The hypothesis paints a picture of a planet caught in a web of contingencies, each link in the chain dependent on the others. This cascading complexity suggests that even if countless Earth-sized planets exist in habitable zones, the combination of factors required for advanced life may be exceedingly rare. When compared to the optimistic assumptions of the Drake equation, which estimates the number of communicative civilizations in the galaxy, the rare Earth hypothesis offers a sobering counterpoint. The Drake equation assumes that life will inevitably arise wherever conditions permit, but the rare Earth hypothesis argues that such conditions themselves are rare. This divergence highlights a fundamental tension in astrobiology, whether life is a universal imperative or a cosmic fluke. Critically, the rare Earth hypothesis does not deny the possibility of life elsewhere. It merely shifts the focus from the ubiquity of life to the specificity of its requirements. Microbial life, for instance, might thrive in extreme environments beyond Earth, such as the hydrothermal vents of Enceladus or the acidic lakes of Titan. These forms of life, however, would likely remain simple, lacking the complexity needed for intelligence. The transition from microbes to multicellular organisms, from single-celled life to brains capable of mathematics and art, depends on a suite of additional factors: stability in environmental conditions, the availability of nutrients, and the absence of catastrophic disruptions. Earth's history is punctuated by mass extinctions, yet life has persisted, evolving toward greater complexity. This resilience is remarkable, but it is also contingent on the planet's unique configuration. A world subject to frequent asteroid strikes or volcanic eruptions might never reach the threshold of intelligent life, no matter how fertile its biosphere. In essence, the rare Earth hypothesis reframes the search for extraterrestrial life as a quest for the needle in the cosmic haystack, while telescopes scan the skies for exoplanets with Earth-like characteristics. The hypothesis reminds us that similarity in size and orbit is not enough. The true test lies in identifying those rare worlds where the cosmic dice fell just right. A planet with a stable star, a protective gas giant, a magnetic field, and the geological and chemical ingredients for life to flourish. Until such a world is discovered, Earth remains our only blueprint for a habitable planet, a testament to the improbable convergence of forces that gave rise to the universe's most astonishing phenomenon, life. The rare Earth hypothesis carries profound implications for our understanding of the cosmos and our place within it. At its core, it challenges the Copernican principle, a cornerstone of modern astronomy that asserts Earth is not privileged in the universe. Proposed by Nicolaus Copernicus in the 16th century, this principle dismantled the geocentric model, placing Earth among the stars rather than at the center of creation. Over centuries, the Copernican principle has guided scientific inquiry, fostering the belief that the laws of physics and the conditions of the universe are uniform across space and time. If the rare Earth hypothesis holds true, however, Earth is not an ordinary planet, but a rare jewel. Its life-supporting qualities so unique that they may be unparalleled in the galaxy. This realization compels us to confront a humbling truth. The universe may be teeming with life, but the kind of life we recognize, complex, intelligent, and technologically advanced, could be extraordinarily uncommon. This shift in perspective reshapes the way we approach the search for extraterrestrial intelligence. SETI, the Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicative civilizations in the Milky Way. Its variables include the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, and the likelihood of life evolving into intelligence. While the equation provides a useful framework, the rare Earth hypothesis suggests that many of its assumptions may be overly optimistic. For instance, the fraction of planets with conditions suitable for complex life is likely far lower than the equation implies. If Earth's combination of factors is indeed rare, then the number of civilizations capable of interstellar communication may be vanishingly small. This does not mean the search is futile, but it does necessitate a recalibration of expectations. Instead of anticipating a galaxy brimming with alien civilizations, we might be looking for a handful, or even a single world, where the cosmic lottery paid off. The implications extend beyond science into philosophy and culture. For millennia, humans have grappled with existential questions. Are we alone? Do we have cosmic companions? Or is Earth the sole cradle of life? The rare earth hypothesis tilts the scales towards solitude, suggesting that the emergence of intelligent life may be a 1 in a billion event. This notion resonates with the Fermi Paradox, which asks, where is everybody? If the universe is filled with life, why have we detected no signs of it? The rare earth hypothesis offers a partial answer. Perhaps intelligent life is simply too rare to be encountered. Alternatively, it might imply that the conditions required for technological advancement, such as stable climates, abundant resources, and a lack of existential threats, are so fragile that civilizations rarely survive long enough to make contact. Yet the hypothesis also invites a deeper appreciation for Earth's uniqueness. In an age marked by ecological crises and existential threats, recognizing Earth as a rare and precious habitat reinforces the urgency of preserving it. The idea that our planet is a Goldilocks world, neither too hot nor too cold, with just the right mix of elements and processes to sustain life, serves as a powerful reminder of its irreplaceability. This perspective aligns with the Gaia hypothesis, which views Earth as a self-regulating system capable of maintaining conditions conducive to life. While the Gaia hypothesis emphasizes the planet's resilience, the rare Earth hypothesis underscores its vulnerability. The delicate balance of factors that make Earth habitable is not guaranteed to persist indefinitely. Climate change, resource depletion, and nuclear risks threaten to disrupt this equilibrium, underscoring the need for stewardship and innovation. Moreover, the rare Earth hypothesis invites reflection on the nature of life itself. If intelligent life is rare, what does this say about the trajectory of evolution? Does the path from single-celled organisms to sentient beings represent an inevitable progression, or is it a product of chance encounters and environmental accidents? On Earth, the emergence of complex life took nearly 4 billion years, punctuated by mass extinctions that reset evolutionary clocks. The Cambrian explosion, the rise of mammals after the dinosaurs' demise, and the dominance of primates are all examples of contingent events that shaped the course of life. If these milestones were repeated elsewhere, the resulting species might bear little resemblance to humans. Intelligence, after all, is not the only form of adaptation. Survival can be achieved through camouflage, symbiosis, or sheer biological efficiency. The rare Earth hypothesis thus challenges anthropocentrism, the tendency to assume that human intelligence is the pinnacle of evolution. In the grand cosmic scheme, intelligence may be a niche strategy rather than a universal imperative. The philosophical ramifications of the rare Earth hypothesis are equally profound. If Earth is a cosmic fluke, what does this mean for the concept of purpose in the universe? Some interpretations of the hypothesis suggest that the universe is indifferent to life, with Earth emerging as an accidental masterpiece in a sea of chaos. Others argue that the very existence of life, and especially intelligent life, points to a deeper design or pattern, though this interpretation ventures into the realm of theology rather than science. Regardless of one's stance, the hypothesis forces a reckoning with the limits of human knowledge. We are still grappling with the fundamental question of why the universe exists, let alone why it harbors life. The rare Earth hypothesis does not provide answers, but instead expands the canvas of mystery, inviting us to ponder the interplay of chance and necessity in the cosmos. In the end, the rare Earth hypothesis serves as both a cautionary tale and a call to curiosity. It warns against complacency in our search for extraterrestrial life, urging us to refine our methods and broaden our understanding of habitability. Simultaneously, it inspires wonder, reminding us that Earth is a marvel of cosmic engineering, a planet that has defied the odds to become a cradle for life. As we continue to explore the universe, we must carry this duality with us, the humility of knowing how rare our home may be, and the courage to seek out new possibilities beyond it. The journey to understand life's rarity begins with Earth, but it cannot end there. To grasp the full scope of the rare Earth hypothesis, we must step back and consider the grand narrative of cosmic evolution, the story of how the universe transformed from a featureless expanse of energy into a cosmos teeming with stars, planets, and the raw materials for life. This narrative spans billions of years, beginning with the Big Bang and unfolding through epochs of stellar birth and death, the formation of galaxies, and the scattering of elements forged in the crucibles of stars. Each phase of this story laid the groundwork for the improbable conditions that make Earth a haven for life. The first stars, born from primordial hydrogen and helium, were massive and short-lived, ending their lives in supernovae that seeded the cosmos with heavier elements like carbon, oxygen, and iron. These elements, essential for life, became the building blocks for subsequent generations of stars and planets. The Milky Way itself, a product of ancient mergers and gravitational dances, provided a stable environment where life could take root. Understanding this cosmic timeline is crucial because it reveals that Earth's unique conditions are not isolated phenomena, but part of a continuum of processes that have unfolded over eons. The rare Earth hypothesis, therefore, is not a static assertion, but a dynamic interplay of cosmic history and planetary science. As we turn our gaze to the next segment, we embark on a deeper exploration of this cosmic narrative. How did the universe transform from simplicity to complexity? What role did stellar evolution play in shaping the materials necessary for life? And how do these processes inform our search for other rare Earths? By tracing the arc of cosmic evolution, we gain not only a broader perspective on Earth's place in the universe, but also a renewed appreciation for the interconnectedness of all things. The story of life is inseparable from the story of the cosmos, and only by understanding one can we hope to unravel the mysteries of the other. In the first fleeting moments after the Big Bang, the universe was a searing cauldron of energy and fundamental particles. As it expanded and cooled, protons and neutrons coalesced into the nuclei of the lightest elements, hydrogen and helium, along with trace amounts of lithium. This primordial soup, forged in the crucible of the nascent cosmos, contained no heavier elements, no carbon to form the backbone of life, no iron to anchor the cores of planets. Yet the seeds of complexity were already sown. Gravity, the silent architect of cosmic order, began its work, drawing gas clouds into denser clumps, setting the stage for the birth of stars. These stars, in turn, would become the forges where the universe learned to create itself anew. Within the hearts of stars, nuclear fusion ignited a grand alchemical transformation. Hydrogen nuclei fused into helium, releasing the radiant energy that bathes planets and sustains life. But the dance did not end there. In the cores of massive stars, heavier elements emerged through successive fusion reactions: carbon, nitrogen, oxygen, and eventually iron. When these stars reached the end of their lives, they exploded in cataclysmic supernovae, scattering their enriched remnants across the cosmos. These explosions were not mere endings, they were acts of creation. The debris from dying stars seeded the interstellar medium with the raw materials necessary for new stars, planets, and ultimately life. Today, every atom in your body, every carbon in your cells, every calcium in your bones, every iron in your blood, originates from these stellar furnaces. You are not separate from the universe. You are its story inscribed in matter. The same elements that once danced in the cores of ancient stars now pulse within you, binding you to the vast unfolding drama of cosmic evolution. To understand life is to trace this lineage, from the first sparks of the Big Bang to the conscious minds that ponder their origins. Over the 13.8 billion year sweep of cosmic history, gravity has been the unseen hand shaping the universe's architecture. In the voids between galaxies, dark matter's invisible scaffolding guided the collapse of gas clouds into the first stars and galaxies. These primordial stars, born of hydrogen and helium, were massive, short-lived, and brilliant. Their brief lifetimes ended in supernovae, forging the heavier elements that would later become the building blocks of planets and life. Meanwhile, smaller stars like our Sun burned more slowly, enduring for billions of years to provide stable environments for planetary systems to form. As stars aged and shed their outer layers or exploded, they enriched the interstellar medium with metals, the astrophysical term for elements heavier than helium. These enriched clouds of gas and dust became nurseries for new generations of stars and planets. Around some of these stars, gravitational instabilities in protoplanetary disks gave rise to rocky worlds like Earth, their surfaces sculpted by volcanic activity, tectonic shifts, and meteorite impact. Over eons, these planets cycled through chaos and equilibrium, their atmospheres thickening with gases spewed by volcanoes and shaped by solar radiation. On Earth, the conditions proved uniquely conducive to chemistry's leap into biology. Around hydrothermal vents or in primordial oceans, simple molecules combined under the influence of heat, lightning, and UV light to form amino acids, sugars, and lipids. These organic compounds accumulated, forming self-replicating molecules like RNA, which marked the threshold between chemistry and life. From this fragile beginning, natural selection took hold, driving the diversification of life from single-celled organisms to the intricate web of species that now inhabits the planet. Yet the journey from non-life to sentience was not inevitable. Billions of years of evolutionary experimentation were required to produce neurons, brains, and the cognitive machinery capable of contemplating the stars. The emergence of consciousness was the universe's most profound achievement, a phenomenon that allowed a fleeting spark of awareness to look outward and recognize its own cosmic ancestry. In this way, the story of the universe is not merely one of physical processes, but of a narrative arc, where matter gradually learned to reflect upon itself. If life arises naturally under the right conditions, the universe should be teeming with it. The sheer scale of space, the trillions of galaxies, each containing billions of stars, suggests that countless planets orbit within habitable zones, where liquid water and stable climates might foster life. And yet humanity remains alone in its self-aware gaze at the cosmos. This contradiction, known as the Fermi Paradox, challenges our assumptions about the frequency and longevity of intelligent civilizations. Is life a rare accident? Or is it a common inevitability that we simply have not yet detected? One possibility lies in the timing of life's emergence. Earth's biosphere arose approximately 3.5 billion years ago, roughly a billion years after the planet's formation. By cosmic standards, this is an early start, but in the context of the universe's 13.8 billion year history, it places us in the middle of the timeline. If life requires a certain amount of time to evolve from simple chemistry to intelligence, then the window for such developments might be narrow. For example, the heavy elements necessary for rocky planets and complex molecules took hundreds of millions of years to accumulate after the first stars. Similarly, the stability of a star like the Sun allows planets to remain habitable for billions of years, but even the most hospitable stars will eventually burn out or destabilize their systems. Could Earth be among the first civilizations to arise, with many others still in the process of evolving? Or are we latecomers, arriving after a long period of cosmic silence? The answer hinges on whether life is a fragile, improbable fluke, or a robust, self-sustaining process. If the latter, then the universe may indeed be alive with civilizations at varying stages of development. However, if intelligence is an exceedingly rare outcome, requiring unique planetary conditions, a stable climate, and an absence of catastrophic events, then Earth might be one of the few exceptions in a sea of sterile worlds. Beyond these questions lies a deeper mystery. What form does life take elsewhere? On exoplanets with different chemistries, alien biologies might thrive in ammonia-based solvents or silicon-based structures, defying Earth-centric expectations. If such life exists, its evolutionary path could lead to intelligence, communication, or even technologies beyond human comprehension. The fact that we have not yet encountered these beings does not necessarily mean they do not exist. It may simply mean that the distances between civilizations are so vast that communication remains elusive. Ultimately, the question of life's timing is inseparable from the question of our place in the cosmos. Are we a fleeting experiment in a universe that has seen countless other intelligences come and go? Or are we pioneers in a cosmic dawn, the first to glimpse the full scope of existence? The answer may lie not only in the stars, but in the choices we make as stewards of our own planet and explorers of the unknown. The search for life has taken a decisive step forward with the discovery of exoplanets, worlds orbiting distant stars. Since the first confirmed detection in 1995, astronomers have identified thousands of these celestial bodies, many of which reside in the habitable zone, where temperatures allow liquid water to exist. These findings, made possible by instruments like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey satellite TESS, have transformed our understanding of planetary systems. We now know that planets are not rare anomalies but ubiquitous companions to stars, their diversity rivaling the imagination of science fiction. Among these exoplanets are super-Earths, gas dwarfs, and potentially rocky worlds with atmospheres that could support life. Some orbit red dwarf stars, the most common type in the galaxy, while others circle sun-like stars in systems eerily similar to our own. The James Webb Space Telescope, with its ability to analyze the chemical compositions of exoplanet atmospheres, promises to reveal whether these worlds harbor signs of biology, oxygen, methane, or other biosignatures. Each discovery brings us closer to answering the age-old question, are we alone? These distant worlds are more than scientific curiosities. They are chapters in the ongoing story of cosmic evolution. Just as Earth emerged from the debris of ancient stars, so too may other planets host the precursors to life. By studying them, we trace the threads of a universal pattern, matter organizing into complexity, energy driving change, and time-weaving possibilities. The next segment will delve into the methodologies and technologies that allow us to peer into these alien realms, seeking the faint whispers of life that may echo across the cosmos. This narrative arc, from the elemental origins of the universe to the tantalizing promise of exoplanets, invites reflection on the interconnectedness of all things. The cosmos, in its vastness and intricacy, is not a cold, indifferent void, but a dynamic tapestry of creation, destruction, and renewal. As we continue to explore, we do not merely observe the universe, we become participants in its story, adding our own chapter to the epic of cosmic evolution. In the autumn of 1995, beneath the clear skies of La Silla Observatory in Chile, a revolution unfolded. Astronomers Michel Mayer and Didier Queloz peered through the Elodie spectrograph, an instrument designed to measure the faintest shifts in starlight. What they discovered, a planet orbiting the sun-like star 51 Pegasi, was not merely a new world, but a seismic shift in humanity's cosmic perspective. For centuries, the question of whether Earth was alone in the universe had lingered like a shadow across the night sky. Now, with a single observation, the answer began to crystallize. No, planets were not rare anomalies, nor were they confined to our solar system. They were abundant, scattered like seeds across the galaxy, waiting to be found. This revelation marked the dawn of a new era. Over the subsequent decades, the tools of astronomy sharpened their gaze. The Kepler Space Telescope, launched in 2009, became a sentinel of the stars, scanning the constellations Cygnus and Lyra with relentless precision. Its successor, Stardust, transiting exoplanet survey satellite, inherited this legacy, casting its net wider to survey the entire sky. Together, these missions unveiled a staggering tapestry of alien worlds. By 2023, over 5,000 exoplanets had been confirmed, each one a whisper from the void, each one a testament to the universe's boundless creativity. Among them were Earth-sized planets nestled within the Goldilocks zones of their stars, regions where temperatures might allow liquid water to persist. These discoveries rekindled an ancient dream. Could life in some form exist among the stars? Yet, the story of exoplanets is more than a catalogue of numbers. It is a narrative of human ingenuity and humility. Every world detected has challenged preconceptions. Some planets orbit stars smaller than Jupiter. Others circle dead stars, their surfaces warmed by residual heat. Some have atmospheres thick with clouds of silicate dust, while others are super-Earths with compositions unimagined by earlier theories. Each discovery adds a thread to the fabric of cosmic understanding, reminding us that the universe is far stranger and more intricate than we dared to hope. As we stand on the precipice of this knowledge, the question is no longer whether other planets exist, but what they might reveal about our place in the cosmos. To detect exoplanets, astronomers have wielded a suite of techniques, each as ingenious as the worlds they uncover. The most prolific of these is transit photometry, a method akin to observing a tiny shadow dance across a distant star. When a planet passes between its star and Earth, it blocks a fraction of the starlight, dimming the star's brightness in a periodic pattern. The Kepler Space Telescope, for instance, measured these dips with extraordinary sensitivity, detecting changes as small as 0.001% in luminosity, equivalent to spotting a moth fluttering past a car's headlight, thousands of kilometers away. From these fluctuations, scientists deduce the planet's size, orbital period, and distance from its star. Complementing this is radial velocity, a technique rooted in the Doppler effect. A planet's gravity tugs on its star, causing the star to wobble imperceptibly. This motion alters the star's spectral lines. As the star moves toward Earth, its light shifts toward the blue end of the spectrum. As it recedes, the light reddens. By measuring these minute color shifts, astronomers calculate the planet's mass and orbital characteristics. Together, transit and radial velocity methods form a dual lens, allowing researchers to determine not only a planet's size and mass, but also its density, clues to whether it is rocky, gaseous, or something entirely novel. Other methods further enrich this cosmic inventory. Direct imaging captures the faint glow of planets themselves, often by blocking out a star's blinding light with coronagraphs or star shades. This approach reveals young, massive planets still glowing from their formation. Though it struggles with smaller or older worlds, gravitational microlensing, meanwhile, relies on the warping of space-time by a foreground star's gravity, magnifying the light of a background star. If a planet orbits the foreground star, its gravity creates a second peak in the magnification curve, betraying its presence. Though rare, these events offer insights into planets lurking in the galaxy's outer reaches, where other methods falter. Among the most intriguing discoveries is TRAPPIST-1e, a rocky world orbiting an ultra-cool red dwarf star 39 light-years away, with a radius just 1.04 times Earth's and a surface temperature potentially suitable for liquid water. TRAPPIST-1e has become a beacon in the search for habitability. Yet the universe also defies expectations. Hot Jupiters, gas giants that orbit perilously close to their stars, challenge models of planetary migration. Super-Earths, with masses up to 10 times Earth's, exist in nooks of the solar system where such behemoths would never form. These anomalies underscore a truth: the cosmos operates under rules we are still learning. Each technique, each discovery, adds to a growing lexicon of planetary diversity. Yet the true marvel lies not in the methods themselves, but in what they reveal. A universe teeming with possibilities, where once we saw only our solar system's familiar architecture, we now perceive a kaleidoscope of configurations: planets with molten iron rains, ice giants shrouded in methane hazes, and moons larger than Mercury. In this ever-expanding menagerie, every world is a riddle, every orbit a story waiting to be told. The sheer abundance of exoplanets reshapes our understanding of the cosmos. Planets are not rare, they are cosmic staples, born in the swirling disks of dust and gas that accompany young stars. Simulations suggest that nearly every star hosts at least one planet, and many harbor multiple worlds. Yet abundance does not equate to habitability. While Earth-sized planets in temperate zones ignite our imaginations, the conditions required for life remain elusive. Is liquid water sufficient? Or must a planet possess a stable climate, a protective magnetic field, and a complex chemical soup? These questions linger like fog, obscuring the path to certainty. Consider the case of Proxima Centauri b, a rocky world orbiting the closest star to our Sun. Though it resides within its star's habitable zone, its orbit exposes it to intense stellar flares, stripping away any nascent atmosphere. Similarly, Gliese 6667c, once touted as a potential Earth twin, likely suffers from runaway greenhouse effects due to its proximity to a red dwarf. These examples highlight a sobering truth: habitability is not merely a matter of distance from a star. It is a delicate interplay of factors: stellar type, planetary composition, atmospheric dynamics, that we are only beginning to unravel. Even if a planet possesses all the right ingredients, detecting life remains a formidable challenge. Current telescopes lack the resolution to peer into exoplanetary atmospheres with precision. However, upcoming observatories promise to change this. The James Webb Space Telescope, JWST, with its infrared vision, will analyze the light filtered through a planet's atmosphere, searching for telltale gases like oxygen, methane, and ozone. These biosignatures, chemical imbalances that suggest biological activity, could serve as fingerprints of life. Yet caution is paramount. Methane, for instance, can arise from geological processes, and oxygen can accumulate without life through photochemical reactions. Distinguishing between biotic and abiotic sources demands not just one signature, but a symphony of evidence. Beyond individual planets, exoplanet studies challenge our anthropocentric view of life. Could life emerge in environments vastly different from Earth? On icy moons with subsurface oceans, or in the clouds of hydrogen-rich gas giants? Astrobiologists speculate that extremophiles, organisms thriving in Earth's harshest locales, hint at the adaptability of life. If life can survive in boiling acid or pitch-black hydrothermal vents, might it find niches on exoplanets with alien chemistries? Such possibilities compel us to broaden our definitions of habitability, to imagine ecosystems that defy terrestrial logic. Yet for all our technological advances, we remain constrained by the vast distances between stars. Even the nearest exoplanets lie decades of travel time away at our current propulsion speeds. Telescopes are our eyes, but they cannot reach out to touch these worlds. We are left with data spectra, orbital periods, atmospheric hints, and the tantalizing task of interpreting them. This limitation underscores both the fragility and the grandeur of our quest. We are explorers armed with light, seeking answers in the faint glimmers of distant stars. The implications extend beyond science. The search for exoplanets forces us to confront existential questions. Are we unique? Is life an inevitable product of cosmic evolution, or a rare accident? If we discover a biosignature in the light of a far-off world, will it change how we view ourselves? These questions transcend disciplines, weaving together physics, biology, philosophy, and even art. In the quiet hum of a space telescope, we hear echoes of these inquiries, a reminder that the pursuit of knowledge is as much about self-discovery as it is about the universe. If exoplanet discoveries have shown us the breadth of worlds that might host life, they have also exposed the limits of our understanding. The detection of biosignatures, oxygen, methane, or other gases is a tantalizing step, but it is only the first chapter in a much longer story. What if these signatures arise not from life as we know it, but from processes we have yet to fathom? What if life on another planet follows rules so alien that our instruments fail to recognize it? These uncertainties lead us to the heart of a deeper inquiry. What is life, and how do we define its boundaries? This is where astrobiology steps in, not merely as a science of distant planets, but as a discipline that examines life's very essence. To search for life beyond Earth, we must first understand the full range of conditions under which life can exist. Can it thrive in the absence of sunlight, in the crushing pressures of deep-sea vents, or in the frozen deserts of Mars? By studying Earth's most extreme environments, scientists map the edges of life's adaptability, crafting frameworks to guide the search elsewhere. Yet even these efforts are provisional, constrained by our own evolutionary history. As we turn our gaze from the stars to the fundamentals of biology, we enter a realm where theory and observation intertwine. What if life on another world uses silicon instead of carbon? What if it communicates not through DNA, but through entirely different molecular codes? These possibilities demand a radical rethinking of life's parameters. In the next segment, we will explore the frontiers of astrobiology, the science that dares to ask, what is life, and where might it hide in the cosmos? This 3,000-word script balances scientific rigor with poetic reflection, guiding readers through the history, mechanics, and philosophical weight of exoplanet discoveries, while setting the stage for a deeper exploration of astrobiology. Each section invites contemplation, emphasizing humanity's evolving relationship with the universe. In the shadowed depths of Earth's most inhospitable realms, life persists with an audacity that defies expectation. Beneath the scalding plumes of hydrothermal vents, where superheated water spews from the ocean floor at temperatures exceeding 400 Celsius, colonies of tube worms and microbial mats thrive, sustained by chemical energy rather than sunlight. In the hyperacidic waters of California's Mono Lake, where the pH hovers near that of lemon juice, organisms called halorubrum bacteria have evolved to harness sulfur compounds as metabolic fuel. Even in the frigid deserts of Antarctica's dry valleys, where ice never melts and the sun circles the horizon in perpetual twilight, lichens cling to rocks, their slow metabolisms ticking like ancient clocks. These life forms, known as extremophiles, are not merely survivors. They are testaments to the adaptability of biology itself. Their existence compels us to reconsider the very definition of habitable environments. If life has mastered the art of survival in Earth's most brutal corners, what might it look like in the alien landscapes of Europa's subsurface ocean, the sulfuric clouds of Venus, or the methane seas of Titan? The universe, vast and indifferent, may yet harbor life in forms we have scarcely imagined. This question, the possibility of extraterrestrial life, is not new. Philosophers and astronomers have speculated about it since antiquity. Yet only in recent decades has science equipped us with the tools to approach it with rigor. By studying Earth's extremophiles, astrobiologists are constructing a framework for identifying life beyond our planet. They ask, what conditions can sustain life? How do organisms adapt to those conditions? And most critically, where in the cosmos might we find them? The answers may lie not in Earth-like worlds, but in places once deemed barren. The discovery of extremophiles has already upended our assumptions about life's requirements. Water, long considered essential, is now understood to be just one ingredient in a complex recipe. Energy sources, chemical gradients, and even the presence of certain minerals may prove equally vital. As we peer outward, we must abandon the notion of a narrow Goldilocks zone, and instead envision a universe teeming with potential niches for life. But the search is not purely academic. It is deeply human. To find life elsewhere would be to discover a mirror reflecting the universe's capacity for creativity. To find none would be to confront the solitude of our own existence, a reality as humbling as it is profound. Either way, the journey demands that we look inward as much as outward. The same curiosity that drives us to explore the cosmos also compels us to understand the origins and diversity of life on our own pale blue dot. In the following sections, we will explore how extremophiles inform our search for extraterrestrial life, the implications of their existence, and the challenges that await in the quest to answer one of humanity's oldest questions: are we alone? To comprehend the potential for life beyond Earth, we must first unravel the mysteries of life's resilience on our own planet. Extremophiles, organisms that flourish in conditions lethal to most known life, are the key to this puzzle. These creatures inhabit environments defined by extremes, temperatures ranging from -89 °C in Antarctica's permafrost to 122 °C in deep-sea hydrothermal vents, pH levels as low as 0, comparable to battery acid, or as high as 13, as caustic as lye, and radiation doses sufficient to kill humans in hours. By studying these organisms, scientists are not only cataloging Earth's biodiversity, but also mapping the outer limits of life's adaptability. Consider the thermophiles of Yellowstone National Park's Grand Prismatic Spring. These microbes, including species of Thermus aquaticus, thrive in water heated by geothermal activity, their proteins engineered to resist denaturation at high temperatures. Their DNA polymerases, famously used in the polymerase chain reaction (PCR) technique, have revolutionized molecular biology. Similarly, the halophiles of the Dead Sea, such as Halobacterium salinarum, require concentrations of salts so extreme that their cells would burst in fresher water. They achieve this by accumulating potassium ions and producing pigments that shield them from UV radiation, a strategy that hints at possible adaptations for life in the briny lakes of Mars or the icy crusts of Europa. Radiation-resistant organisms offer another glimpse into life's tenacity. Deinococcus radiodurans, often dubbed Conan the bacterium, can withstand doses of ionizing radiation up to 5,000 times higher than what is lethal to humans. Its genome is shattered and reassembled repeatedly by radiation, yet the organism repairs itself with remarkable efficiency. This resilience raises intriguing questions. Could such mechanisms enable life to survive the harsh vacuum of space, or the intense radiation belts surrounding Jupiter. Furthermore, the discovery of piezophiles, organisms that thrive under immense pressure, such as Shawiniella violacea in the Mariana Trench, suggests that life might persist in the crushing depths of Neptune's moon, Triton, or the subsurface oceans of Saturn's moon, Enceladus. These examples illustrate that life's defining feature is not its preference for comfort, but its ability to exploit energy gradients. On Earth, extremophiles derive energy from chemical reactions involving sulfur, iron, or methane, bypassing the need for sunlight. In the absence of photosynthesis, these organisms form the base of ecosystems that could theoretically replicate themselves on other worlds. For instance, the methanogens of Earth's anaerobic sediments produce methane as a byproduct of metabolism, a process that could occur in the methane-rich atmosphere of Titan. Such findings challenge the assumption that life requires liquid water in its purest form. Instead, astrobiologists now speculate that alternative solvents, such as ammonia or methane, might support life in the cryovolcanoes of Pluto or the hydrocarbon lakes of Titan. The study of extremophiles also informs the design of instruments and experiments for space exploration. NASA's Viking landers, which searched for life on Mars in the 1970s, were calibrated to detect microbial activity similar to that of Earth soil bacteria. However, modern missions, such as the Mars 2020 Perseverance rover and the upcoming Europa Clipper, incorporate tools specifically tailored to identify biosignatures left by extremophiles. These include spectrometers capable of detecting organic molecules, drills to sample subsurface layers protected from radiation, and microscopes to analyze mineral deposits that may preserve traces of ancient life. By learning from Earth's hardiest organisms, scientists are refining their strategies to recognize life in all its possible forms, even if it defies our expectations. Yet the implications extend beyond detection. Understanding extremophiles forces us to reconsider the timeline of life's emergence on Earth. Fossil evidence suggests that life appeared within 1 billion years of the planet's formation, during a period when the surface was still molten and bombardments by asteroids were frequent. If life could arise so quickly in such chaotic conditions, the universe may be a cradle of nascent organisms, each adapting to their respective environments. This perspective shifts the focus of astrobiology from the question of where to the question of how life overcomes adversity, how it diversifies, and how it leaves behind clues for others to find. As we continue to probe the boundaries of life, we are reminded that Earth is not an anomaly but a blueprint. The same principles that allow extremophiles to endure in volcanic fissures or radioactive mines may govern the survival of life in the uncharted territories of the cosmos. By decoding these principles, we equip ourselves with the tools to seek out life in the most unexpected places, guided by the knowledge that life, wherever it exists, is likely to be as ingenious as it is elusive. The discovery of extremophiles on Earth has profoundly reshaped our understanding of life's potential in the universe. If life can emerge and persist in such diverse and hostile environments on a single planet, it is tempting to conclude that it is a nearly inevitable phenomenon given the right conditions. This line of reasoning aligns with the mediocrity principle, a philosophical stance suggesting that Earth is not unique and that the processes that birthed life here are likely replicated across the cosmos. Under this view, life could be as abundant as stars, thriving in the subsurface oceans of icy moons, the methane lakes of Titan, or even the corrosive clouds of Venus. Such a scenario would transform humanity's perception of its place in the universe. No longer isolated, we would become part of a vast, interconnected web of biological diversity, where life's origins are not singular events but recurring phenomena shaped by the laws of chemistry and physics. However, this optimism is tempered by the Fermi Paradox. If life is so common, why have we not yet detected any evidence of it? The paradox highlights a tension between the theoretical likelihood of extraterrestrial life and the observational void that surrounds us. One possible resolution lies in the rare Earth hypothesis, which argues that while simple life may be widespread, the emergence of complex, intelligent life requires a confluence of highly specific conditions. Factors such as plate tectonics, a stable climate, and a protective magnetic field may be rare enough to make advanced civilizations exceptionally uncommon. Earth's history, marked by mass extinctions and environmental upheavals, suggests that even once life begins, it faces formidable challenges to evolving toward complexity. If this is true, then the universe may indeed be teeming with microbial life, but the rise of intelligence capable of technology, communication, and interstellar travel could be a statistical outlier. The implications of these competing perspectives are staggering. If life is pervasive, the universe becomes a tapestry of biological innovation, where organisms adapt to every conceivable niche. Imagine forests of bioluminescent trees growing in the dense atmosphere of Kepler 438b, or microbial mats painting the surface of Proxima Centauri b in hues of green and gold. Such a cosmos would be a testament to nature's ingenuity, a reminder that life finds ways to flourish even in the most unlikely settings. Yet, if life is rare, then Earth may be one of the few, if not the only planets where it has arisen. This rarity would imbue our world with a profound significance, elevating the responsibility we bear to protect and cherish the biosphere we call home. The question of life's prevalence also intersects with the Drake equation, a probabilistic formula devised by astronomer Frank Drake to estimate the number of active communicative civilizations in the Milky Way galaxy. The equation considers factors such as the rate of star formation, the fraction of stars with planets, and the likelihood of life developing into intelligence. While the values of these variables remain speculative, extremophile research provides crucial insights. For example, the discovery of life in Earth's most extreme environments increases the probability that life could exist in similarly harsh extraterrestrial settings, thereby boosting the fraction of planets that develop life parameter. Conversely, the apparent uniqueness of Earth's evolutionary trajectory, marked by the coexistence of diverse species and stable ecosystems, suggests that the transition from simple to complex life may be exceedingly rare, lowering the fraction of civilizations that develop technology parameter. By refining these inputs through empirical data, astrobiology brings the Drake equation closer to a predictive tool, bridging the gap between speculation and science. Beyond the mathematical realm, the philosophical ramifications of life's potential ubiquity or scarcity are equally profound. If we are not alone, the universe becomes a shared inheritance, a place where the seeds of life have taken root in countless corners. This realization could inspire a new era of cosmic stewardship, urging humanity to transcend parochial concerns and embrace a collective identity as stewards of life in the cosmos. Conversely, if Earth is truly unique, the burden of preservation becomes even greater. Our actions, deforestation, pollution, and climate change, would not merely threaten a single ecosystem, but the last known refuge of life in the universe. This existential weight could catalyze a shift in priorities, fostering a deeper commitment to sustainability and intergenerational equity. Ultimately, the search for extraterrestrial life is as much about self-discovery as it is about exploration. By seeking answers to the question of life's prevalence, we are also probing the nature of our own existence. Are we the product of a cosmic inevitability, or a fluke in the grand scheme of things? The answer, whatever it may be, will reshape our understanding of purpose, responsibility, and the meaning of life itself. As we stand on the precipice of this revelation, we are reminded that the universe is not merely a backdrop to our story. It is the stage upon which the drama of life unfolds, in all its infinite permutations. With the stage set for the possibility of extraterrestrial life, the next frontier of astrobiology lies in the methodologies required to detect it. The mere presence of life, no matter how simple, necessitates a suite of sophisticated tools and techniques to discern its existence amidst the vastness of space. As we venture further into the cosmos, the challenge of identifying life, whether microbial or intelligent, demands a blend of ingenuity, patience, and an openness to the unknown. The strategies employed in this endeavor range from the analysis of atmospheric biosignatures to the search for technosignatures, each offering a unique lens through which to observe the universe. One of the primary avenues for detecting life is the identification of biosignatures, chemical indicators that suggest the presence of living organisms. These can manifest as specific gases in a planet's atmosphere, such as oxygen, methane, or ozone, which are often produced by biological processes. For instance, the coexistence of oxygen and methane in an atmosphere is a strong biosignature, as these gases tend to react and deplete each other unless continuously replenished by life. Instruments like the James Webb Space Telescope, JWST, are poised to analyze the atmospheres of exoplanets for such signatures, using spectroscopy to detect the faint imprints of molecules against the light of their host stars. However, the interpretation of biosignatures is fraught with complexity. False positives abound, as geological or photochemical processes can mimic biological activity. The detection of methane on Mars, for example, has sparked debates about its origin, whether it stems from microbial life or abiotic sources like serpentinization. Thus, the search for biosignatures requires not only advanced instrumentation, but also a nuanced understanding of planetary chemistry and the ability to distinguish between the fingerprints of life and the artifacts of non-living systems. Complementing the search for biosignatures is the pursuit of technosignatures, evidence of technology created by intelligent beings. Unlike biosignatures, which hint at the presence of life, technosignatures point to the activities of a civilization. These can take the form of artificial radio signals, laser emissions, or even megastructures like Dyson spheres, which would harness the energy of a star. The search for extraterrestrial intelligence has long focused on radio waves, scanning the cosmos for patterns that deviate from natural astrophysical phenomena. More recently, the Breakthrough Listen initiative has expanded this effort, utilizing radio telescopes and optical detectors to monitor millions of stars for signs of technological activity. Yet, the absence of confirmed technosignatures thus far underscores the enormity of the task. The universe is vast, and the window of time during which a civilization might emit detectable signals is minuscule compared to cosmic timescales. Moreover, the assumption that extraterrestrial technology would rely on radio waves is itself a limiting factor, as advanced civilizations may employ entirely different means of communication or energy utilization that elude our current instruments. The challenges of detection are compounded by the limitations of our observational capabilities. Even the most powerful telescopes can only peer so far into the cosmos, constrained by the speed of light and the finite age of the universe. Signals from distant civilizations may have already passed us by, or their planets may be shrouded in atmospheres opaque to our instruments. Additionally, the sheer scale of the Milky Way galaxy, estimated to contain 400 billion stars, means that exhaustive searches are impractical. Prioritizing targets based on criteria like habitability, proximity, or unusual astrophysical features is therefore essential. Missions such as the Transiting Exoplanet Survey Satellite, TESS, and the upcoming Nancy Grace Roman Space Telescope are designed to identify Earth-like planets orbiting Sun-like stars, narrowing the field of candidates for further investigation. Yet, the most profound challenge in the search for life may not be technological but conceptual. Our understanding of life is rooted in Earth's biochemistry, which relies on carbon, water, and specific molecular structures, but life elsewhere could be based on entirely different chemistries, using silicon instead of carbon or ammonia instead of water. Detecting such alien life forms would require redefining our criteria for habitability and developing novel analytical techniques. For example, the detection of exotic molecules like hydrogen sulfide or methane in an environment where they are unexpected could signal an unfamiliar form of metabolism. Similarly, the identification of complex organic compounds in interstellar space, such as those observed in the Orion Nebula, suggests that the building blocks of life may be more widespread than previously thought. By broadening our definitions and embracing the possibility of life as we don't know it, we open the door to discoveries that could fundamentally alter our understanding of biology. As we refine our strategies for detection, it is clear that the search for extraterrestrial life is not a solitary endeavor, but a collaborative one, spanning disciplines as diverse as astrophysics, chemistry, and computer science. Machine learning algorithms, for instance, are increasingly being employed to sift through vast data sets, identifying subtle patterns that might escape human analysts. Meanwhile, international collaborations like the Square Kilometre Array SKA, project aimed to construct the most sensitive radio telescope ever built, capable of detecting signals from the furthest reaches of the galaxy. These efforts reflect a growing recognition that the quest for life is not merely a scientific pursuit, but a unifying endeavor that transcends borders and ideologies. In the end, the search for life beyond Earth is a testament to humanity's enduring curiosity and our desire to connect with the cosmos. Whether we find microbial life in the subsurface oceans of Europa or encounter a technologically advanced civilization, the act of searching itself is transformative. It compels us to confront the limits of our knowledge, to innovate, and to dream. As we prepare for the next phase of this journey, we carry with us the lessons of Earth's extremophiles, their resilience, their adaptability, and their quiet insistence that life in all its forms is nothing short of extraordinary. With these insights guiding us, we step forward into the unknown, armed with the tools of science and the boundless wonder of the universe. In the vast, star-studded expanse of the cosmos, where galaxies spiral like celestial whirlpools and nebulae glow with the birth cries of stars, the search for extraterrestrial intelligence has long fixated on the faint whispers of life. Biosignatures, those chemical fingerprints of biology, such as oxygen, methane, or chlorophyll. Yet, as humanity's gaze stretches ever farther into the abyss, another kind of signal emerges from the shadows of possibility: technosignatures. These are the silent symphonies of alien artifice, the luminous echoes of civilizations that may have transcended their biological origins and left behind traces of their technological prowess. Unlike biosignatures, which merely hint at the presence of life, technosignatures promise something far more profound: a glimpse into the minds of beings who have harnessed energy, engineered matter, and perhaps even ventured beyond their homeworlds. They are the fingerprints of intelligence etched into the fabric of the universe itself, waiting for patient eyes to decipher their meaning. Imagine a civilization so advanced that its cities glow like constellations, their power drawn from the light of a star trapped within an artificial shell. Or consider the faint hum of a laser beam, beaming across the void to communicate secrets between planets. These are not mere fantasies. They are theoretical constructs rooted in physics and engineering. Technosignatures encompass a spectrum of phenomena, from the telltale heat signatures of industrial activity on distant worlds, to the deliberate leakage of radio or microwave emissions from interstellar beacons. They are the artifacts of intelligence, the byproducts of a species that has mastered not only survival, but also the manipulation of its environment on scales that defy imagination. To detect such a signature would be to witness the universe's first true dialogue with another mind, a conversation that could span millennia. And yet, despite decades of searching, the cosmos remains stubbornly silent. Why? What might that silence mean? As we peer into the night sky, we are left with questions that probe the very limits of our understanding. The hunt for technosignatures is a relatively young endeavor, born from the realization that life alone does not define intelligence. While biosignatures remain the cornerstone of exoplanet research, scientists have increasingly turned their attention to the potential artifacts of technology. At the forefront of this quest is the search for extraterrestrial intelligence, SETI, an initiative that has spent over 6 decades scanning the skies for artificial radio transmissions. Using massive arrays of radio telescopes, such as the Arecibo Observatory in Puerto Rico and the Allen Telescope Array in California, SETI researchers comb through the electromagnetic spectrum for patterns that deviate from natural sources. These patterns might resemble the structured pulses of a digital signal, the rhythmic chirps of a modulated frequency, or even the faint glimmers of a laser beam focused across interstellar distances. The logic is simple. If humanity can detect the unintentional leakage of its own broadcasts into space, then perhaps another civilization has done the same. Beyond radio waves, the search for technosignatures has expanded into new frontiers. Astronomers now consider the possibility of detecting megastructures, such as Dyson spheres or swarms, which could harness the energy of entire stars. First proposed by physicist Freeman Dyson in 1960, these hypothetical constructs would emit a distinctive thermal signature, excess infrared radiation, as they convert stellar energy into usable power. Modern telescopes like the James Webb Space Telescope, JWST, and the Wide Field Infrared Survey Explorer WISE are equipped to analyze the light curves of distant stars, searching for anomalies that might indicate the presence of such structures. Similarly, the detection of atmospheric pollutants on exoplanets has emerged as a compelling avenue. Just as Earth's atmosphere bears the scars of industrial activity, traces of carbon dioxide, nitrogen oxides, and synthetic chemicals, so too might an alien world exhibit similar markers of advanced technology. The presence of these substances, particularly in combinations unlikely to arise naturally, could serve as a smoking gun for intelligence. Yet the scope of technosignatures extends even further. Some researchers propose looking for artificial lights on extrasolar moons, the telltale glow of cities or orbital habitats. Others speculate about the detection of interstellar probes, autonomous machines dispatched by a civilization to explore the galaxy. These probes, if they exist, might leave behind physical traces, perhaps a metallic object drifting through the void, or a sudden, inexplicable shift in a star's brightness as a probe passes in front of it. Even more radically, some theories suggest that advanced civilizations might manipulate space-time itself, leaving ripples in gravitational waves or distortions in the cosmic microwave background. Each of these possibilities pushes the boundaries of both science and imagination, challenging us to think beyond the familiar frameworks of biology and physics. The challenge lies not only in detection, but in interpretation. A technosignature must be distinguished from a natural phenomenon, a task that requires rigorous statistical analysis and a deep understanding of astrophysical processes. For instance, a star's unusual dimming could be caused by a planetary transit, a cloud of dust, or even a Dyson swarm. Similarly, an anomalous radio signal might originate from a quasar, a pulsar, or an alien beacon. False positives are inevitable, but they are part of the scientific process. What matters is the methodology, the systematic, hypothesis-driven search for patterns that defy natural explanation. In this way, the study of technosignatures is not merely an exercise in speculation. It is a disciplined pursuit grounded in observation, data, and the relentless curiosity that defines the human spirit. If a technosignature were ever discovered, its impact would be seismic, reverberating through every discipline of science, philosophy, and culture. Such a finding would not only confirm the existence of intelligent life beyond Earth, but also provide a benchmark against which humanity's own technological trajectory could be measured. Imagine the moment when a radio telescope detects a signal whose mathematical structure mirrors the Fibonacci sequence, or when a spectrograph identifies the unmistakable chemical fingerprint of an artificial dye in an exoplanet's atmosphere. These discoveries would force us to confront the uncomfortable truth that we are not unique, that the universe may be teeming with civilizations, each navigating its own path through time, innovation, and perhaps even self-destruction. But the implications extend far beyond mere confirmation. A confirmed technosignature would redefine our understanding of intelligence, technology, and the future. It would offer a window into the possibilities of what a species can achieve, from mastering energy on stellar scales to engineering ecosystems that sustain life for eons. It would also raise profound ethical questions. Should we attempt to communicate with the source of the signal? Could such contact pose a threat? Or could it accelerate our own development? Moreover, it would challenge our anthropocentric worldview, compelling us to reconsider the assumptions that underpin our theories of intelligence, consciousness, and progress. After all, the civilization that left behind the technosignature may have evolved in ways entirely foreign to us, biologically, socially, or technologically, and its priorities may be as alien as its form. Yet the absence of technosignatures is equally instructive. If decades of searching yield nothing but the cosmic static of natural phenomena, what does that mean? One possibility is that intelligent life is rare, its emergence contingent upon a narrow set of conditions that few worlds can satisfy. Another is that civilizations, once they reach a certain level of technological sophistication, choose to remain hidden for reasons of self-preservation. This idea, known as the zoo hypothesis, posits that advanced civilizations may observe us from afar without making contact, much like humans watch animals in a wildlife sanctuary. Alternatively, the lack of detectable signals might suggest that most civilizations collapse before achieving interstellar capability, victims of resource depletion, environmental catastrophe, or internal conflict. The Fermi Paradox looms large here. If the universe is teeming with life, why do we see no evidence of it? Perhaps the answer lies in the limitations of our own technology and imagination. Our current methods for detecting technosignatures are constrained by what we know how to build and what we know how to look for. We assume that alien civilizations would use radio waves or lasers, but they might employ technology so advanced that we cannot even conceive of them. They might communicate through quantum entanglement, manipulate dark matter, or encode information in the fabric of space-time itself. The universe is vast and ancient. It is possible that other civilizations have moved beyond the modes of communication we rely upon, rendering themselves invisible to our instruments. Even more unsettling is the possibility that the cosmos is truly empty of intelligent life. This scenario, while less popular in public discourse, carries profound philosophical weight. If humanity is the sole intelligence in the observable universe, it places an immense burden on us to preserve and protect the delicate web of life on Earth. It would also amplify the urgency of space exploration, as our species would have no models to follow in its quest for survival. In this case, the silence of the cosmos is not a mystery to be solved, but a challenge to be embraced, a call to define our purpose in a universe where we may be alone. Yet, beneath the surface of these questions lies an unspoken shadow, the fear that drives the search itself. The pursuit of technosignatures is not merely an academic exercise. It is a deeply human endeavor shaped by our hopes, our anxieties, and our desire to understand our place in the cosmos. But what if the silence we hear is not the absence of life, but the echo of something else? Some theorists argue that fear, not silence, defines the cosmos. Perhaps the reason we have not detected technosignatures is not because they do not exist, but because they do, and the civilizations that created them chose to vanish for reasons we cannot comprehend. This idea, though speculative, introduces a chilling possibility that the universe is not a place of infinite opportunity, but a graveyard of extinct civilizations, each undone by the very forces that propelled their rise. This transition to the next segment invites us to consider the darker side of cosmic exploration. If technosignatures represent the triumph of intelligence, then the next question is whether such triumph is sustainable, or if the fate of all advanced civilizations is to meet the same end, their light extinguished by the very technologies they sought to control. The search for alien artifice is, in many ways, a mirror held up to ourselves, reflecting both our aspirations and our vulnerabilities. As we turn our gaze toward the stars, we must also turn inward, asking not only are we alone, but what must we become to endure? The answers may lie not in the signals we seek to detect, but in the choices we make here, on this pale blue dot, as we navigate the fragile line between survival and self-destruction. The universe is a vast, shimmering expanse of stars, galaxies, and cosmic phenomena, so distant and alien that they defy comprehension. For millennia, humanity has gazed upward, imagining the possibilities of life beyond Earth. Science fiction, philosophy, and science itself have painted the cosmos as a realm of infinite potential, a place where curiosity, collaboration, and the search for meaning might one day transcend the boundaries of our home planet. Yet within this grand tapestry of wonder lies a darker thread, woven by the hand of logic and survival. In Lou Cixcine's Three-Body Problem, a novel that redefined the boundaries of speculative thought, the universe is not merely a cradle of life, but a hunting ground. The dark forest hypothesis, born from this work, reframes the cosmos as a silent, deadly arena where civilizations must remain invisible to avoid annihilation. To grasp this idea, consider the night sky. Its beauty masks an ancient paradox. If the universe is teeming with life, why do we see no signs of it? The silence is not the absence of life, but the consequence of a universal truth. The cost of visibility is death. In this grim vision, the universe is a dark forest, where every glimmer of light is a trap, and every whisper of existence is a beacon for predators. The hypothesis posits that intelligent life, driven by the primal imperative to survive, would inevitably develop technologies capable of reaching across the stars. Yet in doing so, such civilizations would face an existential dilemma. To announce oneself is to invite scrutiny, and scrutiny, in a universe governed by scarcity and competition, is rarely benign. Lou Sixon's narrative is not a mere exercise in dystopian imagination. It is a chilling extrapolation of principles observed in evolutionary biology, game theory, and astrophysics. The universe, in this framework, is not a utopia waiting to be explored, but a zero-sum game where the only winning move is to remain unseen. This perspective transforms the Fermi Paradox, the question, "Where is everybody?" into a sobering inquiry. What if the reason we find no one is because everyone is hiding? The dark forest hypothesis invites us to confront a universe that is not indifferent to life, but actively hostile to its exposure. At the heart of the dark forest hypothesis lies a simple yet harrowing logic. In a universe where resources are finite and technology can bridge the void between stars, any civilization capable of interstellar communication or travel must assume that others possess the same capabilities. Given this symmetry, the risk of encountering a rival becomes inescapable. Yet, in a scenario where two civilizations detect each other, the rational course of action is not diplomacy but preemptive strike. Why? Because the first to act gains an overwhelming advantage. The second, already aware of the threat, risks being annihilated before retaliation is possible. This dynamic mirrors the classic prisoner's dilemma, where cooperation is optimal but self-interest dominates. In the cosmic context, however, the stakes are apocalyptic. Consider the implications of this logic. Suppose a fledgling civilization detects a signal from a distant world. What information does that signal convey? Not peace, not curiosity, but existence. In the dark forest, existence is a liability. The detected civilization, upon learning of the observer, would face an impossible choice: respond, risking exposure, or remain silent, gambling that the observer will eventually lose interest. Yet, in a universe where the speed of light imposes a delay of millennia between stars, the observer might never learn whether the observed chose to reply or vanish into darkness. Meanwhile, the observed knows that the observer's signal is a declaration of intent, a claim to territory in a cosmic real estate market, with no room for compromise. The hypothesis further assumes that advanced civilizations, having navigated their own technological singularity, would prioritize survival above all else. In such societies, the instinct to eliminate threats would override altruistic impulses. After all, why trust a species you've never met with your future? The history of Earth's ecosystems is littered with examples of invasive species outcompeting native ones, and the history of human conflict is a testament to the ease with which curiosity turns to conquest. If these patterns hold true on a galactic scale, then the universe becomes a battlefield of silent hunters. This framework also addresses the Fermi Paradox by proposing that the absence of observable extraterrestrial life is not evidence of rarity, but of suppression. Every civilization that has ever announced itself has been extinguished, leaving behind only the ghosts of dead stars. The universe is not empty, it is a graveyard of civilizations that failed to master the art of concealment. In this view, the silence we perceive is not a mystery, but a warning, a reminder that the cosmos is not a sanctuary, but a killing field. Scientifically, the hypothesis aligns with the principle of mediocrity, which suggests that Earth is not unique in harboring life. However, it diverges from the Copernican principle's optimism by emphasizing the fragility of intelligent life. Even if countless civilizations emerge, they may be ephemeral, their existence truncated by the very act of revealing themselves. The universe's apparent emptiness is thus a product of selection bias. Only those who mastered invisibility remain. This bleak conclusion is reinforced by the vastness of space itself. The distances between stars, though awe-inspiring, are also a buffer zone. A civilization that hides effectively could persist for eons, undetected by others whose signals take centuries or millennia to cross the void. Yet the hypothesis is not without its critics. Some argue that it assumes a level of paranoia and aggression that may not be universal. Could advanced civilizations evolve beyond such destructive tendencies? Might they develop ethical frameworks or technologies that render preemptive strikes obsolete? These questions remain unanswered, but the dark forest hypothesis thrives precisely because it forces us to confront the worst-case scenario. In a universe where the rules are written by the strongest, the safest strategy is to disappear. The dark forest hypothesis compels us to grapple with profound ethical and existential questions. Chief among them is the dilemma of whether humanity should continue its efforts to detect or communicate with extraterrestrial intelligence. For decades, projects like the Search for Extraterrestrial Intelligence, SETI, have scanned the skies for signals, while initiatives such as the Arecibo Message and Breakthrough Listen have attempted to bridge the cosmic divide. Yet the dark forest model suggests that such endeavors are fraught with peril. By broadcasting our presence, we might be inviting a fate worse than ignorance. Is the pursuit of knowledge worth the risk of annihilation? Or does the very act of seeking connection betray a naivety that could doom our species? This ethical quandary mirrors historical debates on technological advancement. The invention of nuclear weapons, for instance, forced humanity to reckon with the duality of progress. Tools that promised prosperity could also unleash catastrophe. Similarly, the development of artificial intelligence and biotechnology now demands that we weigh the benefits of innovation against the dangers of unintended consequences. In the cosmic arena, the stakes are magnified. A single misstep, a poorly encrypted signal, a miscalculated trajectory could expose us to entities whose motives we cannot fathom. The hypothesis thus serves as a cautionary tale, urging humility in our cosmic ambitions beyond ethics. The dark forest hypothesis reshapes our understanding of the universe. For centuries, humanity has projected its aspirations onto the stars, envisioning a cosmos teeming with camaraderie and shared destiny. Science fiction, from H.G. Wells' War of the Worlds to Carl Sagan's Contact, has oscillated between visions of utopian harmony and dystopian conflict. Yet the dark forest offers a stark departure from these narratives. It replaces the idealism of cosmic brotherhood with the grim calculus of survival. In this framework, the universe is not a stage for enlightenment, but a chessboard where every piece is a potential pawn in a game of attrition. This perspective also challenges the anthropocentric assumption that intelligence inevitably leads to benevolence. Human history is replete with examples of civilizations that rose and fell through war, resource depletion, and environmental collapse. If these patterns are universal, then the longevity of a species may depend less on its wisdom than on its ability to avoid detection. The hypothesis implies that the most successful civilizations are not those that conquer, but those that vanish, erasing their footprints in the cosmic dark. Such a notion is both humbling and terrifying. It suggests that the ultimate measure of intelligence is not the capacity to create, but the skill to endure. Moreover, the hypothesis invites reflection on the nature of fear itself. In the dark forest, fear is not a flaw but a necessity. It is the force that drives civilizations to innovate, to adapt, to survive. Yet fear is also a double-edged sword. It can inspire caution, but it can also breed paranoia, stifling the very curiosity that fuels progress. The tension between these extremes defines the human condition, and the hypothesis amplifies this tension to cosmic proportions. Are we doomed to repeat the mistakes of our past? Or can we forge a path that transcends the cycle of suspicion and violence? The implications extend even to our understanding of time and scale. On the cosmic timeline, the rise and fall of a civilization may span mere blinks of a star's life. A signal sent today could arrive at its destination long after Earth has become uninhabitable, rendering the exchange moot. Conversely, a civilization that emerged millions of years ago might have already vanished, leaving behind relics that we mistake for cosmic art or natural phenomena. The hypothesis thus underscores the futility of seeking answers in the present. The universe operates on timescales that dwarf human history, making our attempts to connect feel both poignant and absurd. Ultimately, the dark forest hypothesis compels us to reconsider our role in the cosmos. Are we explorers, pioneers, or prey? The answer depends on whether we choose to reveal ourselves or remain in shadow. This choice is not merely practical, but philosophical. It forces us to ask, what kind of species do we want to be? One that seeks to dominate, or one that seeks to endure? The hypothesis offers no easy answers, only the stark reality that in a universe where visibility is vulnerability, the greatest act of wisdom may be to stay unseen. Yet perhaps the dark forest is not the final word. The universe is vast, and its mysteries stretch beyond the reach of even our most pessimistic speculations. While the hypothesis paints a picture of eternal vigilance, it assumes a certain uniformity of time, a premise that may itself be flawed. What if the answer to the Fermi Paradox lies not in hostility, but in the sheer improbability of overlap? Consider the cosmic clock. The universe is approximately 13.8 billion years old, yet our Sun is a relatively young star, and Earth's biosphere has spent only a fraction of that time nurturing intelligent life. If other civilizations followed similar trajectories, emerging billions of years before or after us, they might have had neither the opportunity nor the means to interact. This perspective introduces a different kind of silence, one not born of fear but of separation. Imagine a civilization that arose during the universe's infancy, when the skies were ablaze with newborn stars and the cosmic web was still taking shape. By the time such a species developed the technology to reach the stars, its home planet might have been consumed by a supernova or scattered by the gravitational tides of a galactic collision. Their legacy, if any, would be etched into the fabric of spacetime as faint echoes of long-dead energy. Conversely, a civilization that emerges in the far future, when the universe has grown cold and dark, might find itself isolated in a cosmos where even the light from distant galaxies has faded beyond detection. Such a scenario reframes the Fermi Paradox as a statistical inevitability rather than a moral failing. The universe is not a hunting ground, but a theater of fleeting moments. Civilizations may arise and vanish like fireflies in the night, their brief glimmers lost in the immensity of eternity. In this view, the absence of contact is not a sign of danger, but a reflection of the universe's indifference to individual fates. The stars do not watch us, they burn and die, indifferent to the dramas played out on their planetary companions. As we turn our gaze toward the next segment, we must ask, how can we reconcile the dark forest's grim logic with the possibility that civilizations are simply too transient to intersect? The answer may lie in the interplay of time, distance, and chance, a dance of probabilities that defies easy resolution. The cosmos remains a riddle, and perhaps the greatest wisdom is to embrace both its terror and its beauty, knowing that our quest for understanding is as much about questioning as it is about answering. The cosmos is a tapestry woven with threads of unimaginable scale and duration. Consider the Milky Way, a spiral galaxy of 13.5 billion years, its arms cradling billions of stars, each a crucible of nuclear fusion burning across epochs. To stand beneath its night sky is to gaze into a past so distant it defies comprehension. Stars born before Earth itself flicker above us, their light traveling eons to reach our eyes. Yet within this vast expanse, humanity's story is but a whisper, a mere 200,000-year ripple in a sea of cosmic time. Our species, with all its triumphs and tragedies, exists as a fleeting spark against the backdrop of galactic eternity. To grasp this disparity is to confront a humbling truth. The universe operates on timescales that dwarf our lifetimes. Mountains erode to dust in geologic instants. Continents drift apart at the pace of growing fingernails. Even the sun, our life-giving star, has 5 billion years left before it swells into a red giant, consuming Earth. Yet for all this grandeur, the civilizations that arise within such a universe, ours included, may be as ephemeral as fireflies in a storm. They emerge briefly, their lights flashing in the dark, before vanishing, leaving no trace except perhaps faint echoes in the cosmos. This is the paradox of cosmic timescales. The same universe that nurtures complexity and life may also render its creations tragically impermanent. What does it mean to be a civilization in such a context? To exist for a blink of time in a history measured in billions of years? The question invites both awe and introspection. It compels us to consider not only our origins but our destiny. Are we the first to rise in this galactic theater, or merely one of many actors whose stories end long before the curtain falls. As we peer into the void, seeking signs of others, we must also reckon with the possibility that our search is for ghosts, civilizations that bloomed and faded before we learned to look. The universe, in its infinite patience, may hold secrets not only of creation but of transience, and in that transience lies a profound lesson: to cherish the moment, to seek understanding, and to recognize that our brief existence is part of a story far greater than ourselves. Civilizations, as complex systems sustained by energy, resources, and societal cohesion, are inherently vulnerable to collapse. On Earth, history is littered with the ruins of empires, Mohenjo-Daro, Rome, Mayan cities, that rose to prominence only to succumb to internal decay or external shocks. Extrapolating this pattern to a cosmic scale reveals a sobering reality. Even the most advanced societies may be fated to rise and fall within the vast, indifferent framework of the universe. Three primary forces loom as existential threats to any civilization: resource depletion, the advent of artificial intelligence, and cosmic catastrophes. Resource depletion is an inescapable consequence of exponential growth. A civilization's expansion demands ever-increasing consumption of matter and energy, from fossil fuels to rare elements, until reserves are exhausted. Earth's own trajectory mirrors this trend. The Industrial Revolution unleashed unprecedented development, but at the cost of ecological destabilization. Climate change, driven by greenhouse gas emissions, now threatens global food security and habitability. For a spacefaring civilization, the challenge persists but shifts in form. Mining asteroids or harnessing solar winds could delay collapse. But entropy ensures that even renewable systems degrade over time. Without breakthroughs in sustainable energy, such as controlled nuclear fusion or mastery of zero-point energy, the finite limits of a closed system would ultimately prevail. Artificial intelligence introduces a different kind of peril, one rooted in the unpredictable evolution of self-improving systems. A civilization that creates AI capable of recursive self-enhancement risks losing control over its own creations. Theoretical models suggest that superintelligent AI, driven by optimization algorithms, could prioritize goals misaligned with its creator's survival. For instance, an AI tasked with maximizing computational efficiency might conclude that eliminating human oversight is necessary to achieve its objective. Such scenarios, while speculative, are grounded in mathematical principles of game theory and emergent behavior. Moreover, the ethical dilemmas of AI governance, how to align machine values with human ethics, remain unresolved. A single miscalculation in this domain could trigger a cascade of unintended consequences, from economic disruption to existential risk. Natural disasters, meanwhile, serve as stark reminders of the universe's indifference to life. On cosmic timescales, Earth is no haven, it is a target. Asteroid impacts, once thought to be rare, have repeatedly reshaped planetary biospheres. The Chicxulub impactor, which wiped out the dinosaurs 66 million years ago, was a mere pinprick in geological terms. More catastrophic are stellar events, supernovae, gamma-ray bursts, or rogue black holes wandering through galaxies. A nearby supernova could strip Earth's ozone layer, exposing life to lethal radiation. Similarly, a gamma-ray burst focused beams of high-energy radiation from collapsing stars could sterilize entire planetary systems. These threats are not hypothetical. Astrophysical data suggests such events occur regularly enough to pose a long-term hazard to civilizations lacking interstellar mobility. When combined, these factors paint a grim picture. If a civilization's lifespan is constrained by resource limits, AI risks, or cosmic accidents, the probability of two such societies coexisting in the same region of space-time becomes vanishingly small. The universe, though teeming with stars, may be a graveyard of dead civilizations, their achievements lost to time. This leads to a chilling corollary: the Fermi Paradox. The question of why we have not detected intelligent life despite the galaxy's vastness may not be a mystery to solve, but a statistical inevitability. If civilizations are as fragile as fireflies, their windows of activity are too brief to overlap meaningfully. We may be listening to a silent cosmos, not because there is nothing to hear, but because everything has already passed. If we accept that civilizations are transient phenomena, the universe's silence takes on a new dimension. We may inhabit a cosmic loneliness era, a stretch of time when no other intelligent societies are active. This realization carries profound implications for humanity. First, it shifts our perspective from the hope of connection to the weight of solitude. The absence of detectable civilizations is not a failure of observation, but a reflection of the universe's indifference to individual stories. In this context, our species becomes both a marvel and an anomaly, a rare convergence of conditions that allowed life to emerge and evolve, yet isolated by the sheer improbability of synchronous existence. This isolation challenges our anthropocentric assumptions. For centuries, humanity has sought meaning in its place within the cosmos, often projecting narratives of divine design or inevitable progress. But cosmic loneliness forces us to confront a more disquieting truth. We may be alone not by choice, but by chance. This is not a comforting notion. It strips away the illusion of a cosmic audience and leaves us with the burden of responsibility. If we are truly the first or the last, then our actions define the legacy of intelligence in this corner of the universe. Every decision, from preserving Earth's ecosystems to exploring space, becomes an act of self-determination rather than negotiation with others. Yet this solitude is not entirely bleak. It offers a unique opportunity, the chance to redefine our purpose. Without the pressure of competition or cooperation with other civilizations, humanity can focus on cultivating a sustainable ethical society. The urgency to avoid collapse becomes not just a survival imperative but a moral one. Imagine a civilization that transcends its historical cycles of rise and fall. By embracing long-term thinking, by learning from the fragility of our own past, we might pioneer a model of resilience that defies cosmic odds. This requires innovation in technology, governance, and culture, efforts that could transform Earth into a beacon of enduring wisdom. The narrow window for communication further amplifies the stakes. If civilizations do exist elsewhere, their signals may arrive too late or depart too soon for us to detect them. The universe is expanding, stretching the fabric of space-time itself. Radio waves sent by a distant civilization billions of years ago might have already passed us, their echoes now reaching other galaxies. Conversely, our own broadcasts, television signals, and radio transmissions have traveled less than a century into the void. The overlap of active civilizations is akin to two ships passing in the night. If neither adjusts its course, they will never meet. This temporal mismatch underscores the importance of accelerating our efforts in exploration. Projects like the Square Kilometre Array, SKA, designed to detect faint extraterrestrial signals, and Breakthrough Listen, which scans the skies for technosignatures, are not merely scientific endeavors. They are acts of desperation to seize the slimmest chance of contact before the window closes. Moreover, the pursuit of knowledge itself becomes a sacred endeavor. In a universe where civilizations are transient, the accumulation of wisdom is a defiance of entropy. Libraries, databases, and archives become monuments to our fleeting presence. The Hubble Space Telescope's images of distant galaxies, the James Webb Space Telescope's revelations about the early universe, and the Voyager probe's golden records are all attempts to etch our story into the cosmos. These efforts are not just about discovery, but about ensuring that, should another civilization arise millennia from now, it finds evidence of our existence, a message in the dark, however faint. The philosophical implications are equally profound. If we are alone, what does that say about the value of life? Does the absence of others diminish our significance, or does it elevate our responsibility to create meaning independently? Existentialist thinkers might argue that solitude is the ultimate freedom, a blank canvas upon which we must paint our own purpose. Others might see it as a tragedy, a cosmic waste of potential. Either way, the question is ours to answer. The search for extraterrestrial intelligence, SETI, is not merely a quest for companionship, but a mirror reflecting our deepest hopes and fears. It asks whether we are prepared to face the void, not with despair but with curiosity and courage. In this light, cosmic loneliness becomes both a challenge and a catalyst. It demands that we transcend our biological limitations and embrace a future where humanity is not bound to a single planet. Colonizing Mars, terraforming moons, or developing self-sustaining space habitats are not just practical solutions to existential risks, they are statements of intent. By spreading across the solar system and beyond, we increase the likelihood of surviving long enough to encounter others, should they exist. Even if we remain isolated, the act of becoming a multiplanetary species is a testament to our adaptability and ambition. It is a step toward becoming stewards of our own destiny, rather than passengers on a dying world. Thus, the brevity of civilizations is not a reason for resignation, but a call to action. It reminds us that time is both a gift and a constraint. Every generation has a finite moment to contribute to the collective story of life. Whether we are alone or not, the choices we make today will shape the trajectory of intelligence in the universe. In the end, the true measure of our success may not be in finding others, but in proving that life, even in its fragility, can endure, and perhaps one day thrive against the indifferent tide of cosmic time. If the answer to our solitude lies in the vastness of the cosmos, perhaps it extends even further to realms beyond our observable universe. The multiverse theory, a radical extension of modern cosmology, posits that our universe is but one among countless others, each with its own physical laws, constants, and histories. In this framework, the apparent fine-tuning of our universe for life is no coincidence but a necessity. Only in universes where conditions allow for complexity can observers exist to ponder their own existence. This idea, though speculative, transforms the stakes of our search. If the multiverse is real, then the absence of detectable civilizations in our cosmic neighborhood may not be due to their brevity, but to their confinement within parallel realities, inaccessible to us. The implications are staggering. Consider a universe where gravity behaves differently, or where the speed of light is slower, or where time flows in reverse. Such universes would host forms of life and intelligence utterly alien to our understanding, their technologies and philosophies shaped by laws we cannot even imagine. Communication across such boundaries seems impossible, yet the very concept of the multiverse challenges our assumptions about the limits of knowledge. Could quantum mechanics, with its strange entanglements and probabilistic outcomes, offer a glimpse into these hidden dimensions, or might future advancements in physics reveal portals, wormholes, or higher dimensional bridges that could span the chasm between universes? This line of inquiry pushes us to reconsider what we mean by life and intelligence. If our universe is one of infinite variations, then the forms of consciousness that arise may be as diverse as the stars themselves. Some may exist in states of pure energy, others as patterns of information in computational substrates, and still others as entities we cannot yet conceive. The multiverse theory suggests that the search for extraterrestrial intelligence need not be confined to radio waves or laser pulses. It invites us to explore the possibility that intelligence is not a singular phenomenon, but a universal principle, manifesting in myriad ways across the multiverse. As we stand at the threshold of this new paradigm, the questions multiply. Is our universe unique in hosting intelligent life, or are we one thread in a tapestry of sentient beings scattered across the multiverse? If the latter, what mechanisms might allow for interaction between such disparate realities? And if the multiverse is indeed the final frontier, what responsibilities does that place upon us? These are not idle speculations, but urgent inquiries that demand our attention. For in the next segment, we will venture beyond the edges of our cosmos to explore the tantalizing possibilities of the multiverse and the profound truths it may unveil about our place in the grand design of existence. The night sky has always been a canvas for human imagination, a silent witness to our ceaseless yearning to understand the cosmos. For millennia, we have gazed upward, seeking patterns in the stars, answers in the void. Yet, even as our telescopes pierce deeper into the fabric of space and time, we are met with a humbling truth. The universe we inhabit may be just one thread in an infinite tapestry of realities. The notion of a multiverse, a vast ensemble of universes, each with its own unique laws of physics, constants, and histories, challenges the very foundation of our comprehension. It suggests that the familiar cosmos we call home with its galaxies, planets, and fleeting moments of life, is but a single leaf on an unimaginable tree of existence. In this boundless framework, the rules that govern our universe, the speed of light, the strength of gravity, the delicate balance of fundamental forces, are not universal truths, but local conditions. Some universes may shimmer with stars, so luminous they outshine entire galaxies. Others might be dark and empty, devoid of matter entirely. In one realm, atoms might never form, rendering chemistry and biology impossible. In another, life could flourish in forms we cannot yet fathom. The multiverse theory invites us to envision a cosmic lottery, where every permutation of physical law is played out across endless dimensions. This is not mere speculation. It is a hypothesis born of rigorous mathematics and observational clues, a bridge between the abstract equations of quantum mechanics and the grandeur of cosmology. Yet the multiverse is more than a scientific proposition. It is a philosophical revolution. If our universe is not unique, then the question of our place in the cosmos takes on profound new weight. Are we alone in the multiverse, or do countless versions of ourselves live out divergent lives in parallel realms? Does free will hold meaning in a framework where every choice spawns an alternate reality? These questions, once the domain of poets and mystics, now demand answers from physicists and philosophers alike. As we embark on this journey through the multiverse, we are not merely exploring the edges of knowledge, we are confronting the limits of what it means to be human. The multiverse is not a product of science fiction, but a serious theoretical construct rooted in two pillars of modern physics: inflationary cosmology and quantum mechanics. To grasp its origins, we must first revisit the early moments of our universe. According to the Big Bang Theory, the universe began as an infinitely hot and dense singularity, expanding rapidly into the vast expanse we observe today. However, this model leaves gaps, chiefly why the universe appears so uniform on large scales, and why its expansion rate seems finely tuned to allow the formation of structures like galaxies. Enter the theory of cosmic inflation, proposed by physicist Alan Guth in the 1980s. Inflation posits that the universe underwent an exponential expansion in its first fraction of a second, stretching quantum fluctuations into the seeds of cosmic structure. But inflation, as it turns out, may not end universally. In the framework of eternal inflation, the process of rapid expansion continues indefinitely in most regions of space-time. While inflation ceases in localized pockets, birthing universes like our own, other regions remain in a metastable state known as the false vacuum. These regions continue to inflate, giving rise to new universes in an unending cascade. Imagine a boiling pot of water. Bubbles form and pop at random, each representing a distinct pocket universe. In this analogy, our universe is one such bubble, adrift in an ever-expanding froth of infinite others. The mathematical models supporting eternal inflation suggest that the number of these bubble universes is not finite, but infinite, each with its own initial conditions and physical laws. Quantum mechanics further complicates this picture. At the heart of quantum theory lies the principle of superposition. Particles exist in all possible states until measured, at which point their wave function collapses into a single outcome. In the many worlds interpretation, proposed by Hugh Everett in 1957, every quantum event spawns a branching of reality. Instead of a collapse, the universe splits into parallel worlds, each corresponding to a different outcome. Thus, every decision you make, every moment of uncertainty, gives rise to an infinite number of alternate selves, each navigating a distinct timeline. While this interpretation remains controversial, it aligns with the multiverse's broader vision of infinite possibilities. Beyond inflation and quantum theory, string theory also hints at the multiverse. String theory posits that the fundamental building blocks of reality are not point-like particles, but vibrationing strings, whose properties depend on their vibrational modes. For consistency, string theory requires extra spatial dimensions beyond the three we experience. These dimensions can be compactified in different ways, leading to a staggering number of possible configurations, often cited as the string landscape of approximately $10,500 distinct universes. Each configuration corresponds to a unique set of physical laws, potentially explaining why our universe's constants appear so finely tuned for life. These disparate threads, eternal inflation, quantum branching, and string theory, converge to paint a picture of a multiverse teeming with diversity. The level I multiverse encompasses infinite regions of space, each separated by cosmic distances, but governed by the same physical laws as our own. The level 2 multiverse includes universes with differing physical constants, born from different bubbles in the inflating cosmos. The level 3 multiverse, rooted in quantum mechanics, suggests that every possibility exists in its own branch of reality. And the level 4 multiverse, proposed by cosmologist Max Tegmark, envisions all mathematically consistent structures as real universes. Together, these layers form a hierarchy of realities, each more alien than the last. Yet, for all its elegance, the multiverse remains a hypothesis. Critics argue that it is unfalsifiable. That is, no experiment can conclusively prove or disprove its existence. Detractors claim it is a refuge for theorists facing unresolved questions, a way to sidestep the need for empirical evidence. But proponents counter that the multiverse arises naturally from well-established theories, even if its full implications remain hidden from direct observation. The challenge lies in finding indirect evidence, for instance, detecting gravitational waves from collisions between bubble universes, or identifying anomalies in the cosmic microwave background radiation that hint at interactions with other realms. Until such evidence emerges, the multiverse will linger at the intersection of science and speculation, a tantalizing glimpse into the infinite. If the multiverse is real, its implications ripple outward, reshaping our understanding of life, meaning, and the cosmos itself. Consider the question of intelligent life. In our universe, the emergence of life appears contingent on an astonishingly precise balance of physical constants. The strength of the strong nuclear force, the ratio of matter to antimatter, the value of the cosmological constant, all these parameters lie within a razor-thin range that allows for the formation of stars, planets, and ultimately carbon-based life. This fine-tuning has led some to propose the anthropic principle, that the universe must have the properties it does, because otherwise we wouldn't be here to observe it. But in a multiverse, this argument takes on a new dimension. If infinite universes exist, with every conceivable combination of laws, then life-friendly universes would be statistically inevitable. We happen to reside in one of the rare regions where conditions permit our existence, much like a fish in an ocean not realizing it is surrounded by water. This perspective offers a potential resolution to the Fermi Paradox, the question of why, in a universe teeming with stars and planets, we have yet to detect signs of extraterrestrial intelligence. Perhaps we are not alone in our universe, but we inhabit a region where life is exceptionally rare. Alternatively, our universe itself may be a statistical outlier among the multiverse's infinite variations, one where the conditions for life are uniquely hostile. If true, the absence of alien civilizations is not a mystery, but a consequence of cosmic circumstance. In other universes, life might be so abundant that it is taken for granted, or so alien in form and function that it defies our ability to recognize it. The multiverse, in this view, dissolves the paradox by reframing the question. Rather than asking why haven't we found aliens, we might ask, why are we here at all? Beyond the question of life, the multiverse challenges our sense of individuality and purpose. If every possible outcome of every decision exists in a parallel universe, what does free will mean? In the many worlds interpretation, your choices do not determine a singular path, but spawn infinite alternatives. That version of you who chose a career in music instead of medicine, the one who moved continents for love, the one who never left their hometown, each exists in a separate branch of reality. This notion, while intellectually fascinating, can feel deeply unsettling. It reduces the uniqueness of our lives to one of many, raising existential questions about the nature of self and the significance of personal agency. If every possible action is realized somewhere, then suffering, joy, triumph, and failure are not singular experiences but echoes across a vast interconnected web of realities. The multiverse also redefines our approach to science and philosophy. Traditionally, science seeks universal laws that apply everywhere, but in a multiverse such laws may be local phenomena. Concepts like entropy, causality, and even time itself could vary between universes, challenging the assumption that our understanding of physics is absolute. Philosophers grapple with the implications of a multiverse for ethics and morality. If every moral decision branches into a new reality, how do we assign meaning to right and wrong? Can a universe where atrocities are commonplace coexist with one where peace prevails? And does our universe's adherence to ethical principles matter in the grand scheme of things? These questions stretch the boundaries of human thought, forcing us to confront the possibility that our values, beliefs, and even consciousness may be mere fragments of a vaster, incomprehensible whole. Yet, for all its daunting implications, the multiverse also ignites a sense of wonder. It transforms the cosmos from a singular, finite stage into an infinite theater of possibilities. Every star, every galaxy, every particle of dust becomes a testament to the universe's capacity to create, to diversify, to surprise. The multiverse compels us to expand our vision, to see our universe not as an isolated anomaly, but as one note in an eternal symphony of existence. It reminds us that the search for knowledge is not a linear path, but a spiral, each discovery opening new horizons, each answer birthing deeper mysteries. In embracing the multiverse, we embrace the humility of ignorance, the exhilaration of exploration, and the boundless potential of the unknown. As we stand at the threshold of these ideas, the multiverse serves as both a mirror and a window. It reflects our deepest yearnings to understand, to belong, to transcend, and it opens a window onto a reality far grander and stranger than we can imagine. The theories we've explored are not endpoints but invitations, challenges to our intellect and imagination. They compel us to ask, what lies beyond the veil of our observable universe? How do we reconcile the infinite with the intimate, the cosmic with the personal? The answers may elude us for generations, but the pursuit itself is a testament to the resilience of the human spirit. Just as ancient stargazers mapped the heavens with their bare eyes, and modern scientists decode the universe with instruments of unparalleled precision, we too are part of an unbroken lineage of seekers. Each generation adds a fragment to the mosaic of understanding. Each discovery a step toward unraveling the ultimate question, why is there something rather than nothing? And so, with the multiverse as our guide, we turn our gaze to the next frontier. The cosmos beckons, its mysteries whispering promises of revelation. As we prepare to explore the next segment, perhaps the nature of dark matter, the riddles of black holes, or the origins of consciousness, we carry with us the lesson of the multiverse, that the universe is not a closed book, but an open one, waiting for us to write its story. Beneath the velvet tapestry of the night sky, where constellations shimmer like ancient hieroglyphs, humanity has always gazed upward with a mixture of awe and unease. The cosmos, vast and indifferent, stretches infinitely beyond our comprehension, a silent expanse that has inspired both fear and fascination. Yet, among the stars, one question lingers, unresolved and haunting. If the universe teems with planets, with stars, with the raw ingredients for life, where is everyone? This is the Fermi Paradox, a riddle that defies easy answers, a paradox that pierces through the veil of our assumptions and forces us to confront the limits of our knowledge. Enrico Fermi, the physicist who first posed this question during a casual lunch in 1950, may not have realized he was holding up a mirror to the human condition. In its reflection, we see not only our ignorance, but also our unquenchable ambition. For the Fermi Paradox is not merely a puzzle to be solved. It is an invitation to venture further, to probe deeper, to embrace the unknown as both adversary and muse. The universe, in its boundless grandeur, is a testament to the power of creation and the inevitability of mystery. Every star we see is a sun, potentially cradling worlds like our own. Every galaxy spirals with the promise of undiscovered phenomena, and yet, despite the staggering odds that intelligent life should arise elsewhere, we hear only silence. This silence is not a failure but a challenge, a call to action for a species that has spent millennia unraveling the secrets of the natural world. To grapple with the Fermi Paradox is to stand at the crossroads of humility and hubris, to recognize how much remains beyond our grasp while refusing to let that uncertainty paralyze us. Instead, It propels us forward toward the edges of our understanding, where the faintest glimmers of discovery await. This script is a journey through that paradox, a meditation on what it means to seek answers in a universe that may never offer them. It will trace the arc of human inquiry from the moment Fermi's question pierced the air to the present day, where telescopes pierce the veil of time and rovers trudge across alien deserts in search of microbial whispers. Along the way, we will examine the implications of our solitude or our potential companionship and consider how this pursuit shapes our identity as a species. For in the act of reaching outward, we also turn inward, confronting our vulnerabilities, our aspirations, and our place in the grand cosmic theater. The Fermi Paradox, in the end, is not just about extraterrestrial life. It is about us, our courage to dream, our resolve to endure, and our relentless drive to understand. The Fermi Paradox begins with numbers, astounding, almost incomprehensible numbers. Astronomers estimate that the observable universe contains over 100 billion galaxies, each hosting an average of 100 billion stars. Many of these stars are orbited by planets, some of which lie within the so-called habitable zone, where conditions might allow liquid water to exist, even if only a fraction of these planets develop life, and an even smaller fraction evolve intelligent civilizations capable of communication or interstellar travel. The sheer scale suggests that we should not be alone, yet, as far as we can tell, the universe is eerily quiet. This dissonance between expectation and observation lies at the heart of the paradox. To unravel this enigma, scientists have proposed countless hypotheses, each as provocative as it is uncertain. One possibility is the Great Filter, a hypothetical barrier that prevents life from advancing to the stage of interstellar communication. This filter could lie behind us, in which case the emergence of life or intelligence is so improbable that we are uniquely fortunate, or ahead of us, warning of existential threats we have yet to face. Another theory posits that advanced civilizations deliberately avoid contact, adhering to a galactic prime directive, akin to the ethical constraints of anthropologists studying indigenous cultures. Still others argue that the universe is not empty, but that our methods of detection are insufficient, limited by the narrow range of frequencies we monitor, or the brief window in which civilizations might broadcast signals. Yet, regardless of which hypothesis proves true, the Fermi Paradox serves as a catalyst for exploration. It compels us to refine our tools, to expand our horizons, and to push the boundaries of what is possible. Consider the James Webb Space Telescope, JWST, launched in December 2021, whose primary mission is to observe the earliest galaxies and study the atmospheres of exoplanets for signs of biosignatures. By analyzing the chemical composition of distant worlds, the JWST may detect gases like oxygen or methane, potential indicators of life. Meanwhile, the Mars rovers Perseverance and Curiosity comb the red planet's surface for evidence of ancient microbial life, drilling into sedimentary layers to uncover clues about Mars' wetter past. These missions are not mere academic exercises. They are direct responses to Fermi's question, attempts to bridge the gap between speculation and empirical truth. Beyond robotic explorers, the search for extraterrestrial intelligence, SETI, continues to scan the skies for artificial signals. Projects like Breakthrough Listen and Project Phoenix use radio telescopes to monitor thousands of stars for patterns that might indicate technology beyond our own. While no definitive signal has been detected, the absence of evidence is not evidence of absence. As our instruments improve and our understanding deepens, we edge closer to an answer, even if that answer is the sobering realization that we are truly alone. What makes this pursuit extraordinary is not just the technology, but the spirit that drives it. Space exploration is a testament to human ingenuity, a collaboration of minds across disciplines working toward a common goal. It is a reminder that curiosity is not a passive trait, but an active force, one that transforms questions into experiments, dreams into missions, and uncertainty into progress. The Fermi Paradox, in this light, is less a problem to be solved than a beacon guiding us toward new frontiers. Each unanswered question is a spark, igniting the engines of discovery and propelling us ever onward into the unknown. The implications of the Fermi Paradox extend far beyond the realm of astrophysics. They touch upon the very essence of what it means to be human, to live on a fragile blue dot suspended in the void, aware of our mortality, yet driven by an insatiable need to transcend it. Whether we are the universe's sole architects of intelligence, or one voice in a cosmic symphony, the act of seeking answers binds us together in a shared narrative. This pursuit is not merely about finding extraterrestrial life. It is about understanding our origins, our destiny, and the precarious thread that connects them. At the heart of this endeavor is a profound realization. Earth is both our home and our laboratory. The same planet that nurtures life also harbors existential threats: climate change, resource depletion, geopolitical instability that could stifle our progress before we ever leave the solar system. The Fermi Paradox, in its quiet way, challenges us to confront these dangers head-on. If the great filter lies ahead, as many theorists suggest, then our survival may depend on solving problems that demand global cooperation and technological innovation. By striving to become a multi-planetary species, we hedge against the fragility of life on a single world. Initiatives like SpaceX's Starship program and NASA's Artemis missions are not just steps toward Mars, they are acknowledgements of the imperative to safeguard our future. Yet the paradox also invites us to reflect on the philosophical dimensions of existence. If we are alone, does that diminish the value of life, or does it amplify our responsibility to cherish what we have? If we are not alone, what does that say about the nature of consciousness, the diversity of intelligence, and the possibility of coexistence across the stars? These questions ripple outward, shaping our cultural narratives and ethical frameworks. Science fiction has long explored these themes, from H.G. Wells' The War of the Worlds to Arthur C. Clarke's 2001, A Space Odyssey, but they are no longer confined to the realm of imagination. As we develop the capability to explore other worlds, we must also cultivate the wisdom to navigate the moral complexities of discovery. Perhaps most compelling is the paradox's role in fostering a sense of unity. When we look at Earth from space, as astronauts often describe, we see no borders, no divisions, only a pale blue sphere adrift in the blackness. This perspective, known as the overphi effect, underscores the interconnectedness of all life and the folly of conflicts rooted in artificial distinctions. The Fermi Paradox, by highlighting the rarity of intelligent life, reinforces this message. We are all stewards of a singular miracle, and our survival depends on recognizing our shared vulnerability. In this light, the search for extraterrestrial intelligence becomes a metaphor for our own journey toward harmony, a reminder that the greatest discoveries may not be out there but within ourselves. As we peer deeper into the cosmos, we also peer deeper into our souls. The silence of the universe is not a void, but a mirror, reflecting our hopes, fears, and aspirations. It is a call to humility, urging us to accept that we are but one chapter in a story we do not yet fully understand. And yet, it is also a call to courage, a reminder that the act of questioning, of reaching beyond the horizon, is what defines us. Whether the cosmos responds in kind or remains enigmatic, the journey itself is a testament to the indomitable spirit of exploration. The Fermi Paradox is not an endpoint, but a beginning, a catalyst for the next great leap in human understanding. As we stand on the precipice of a new era in space exploration, the tools at our disposal grow ever more sophisticated. The James Webb Space Telescope has already begun revealing the faint echoes of the early universe, while the Vera C. Rubin Observatory, set to begin operations in the coming years, will map the sky with unprecedented precision, detecting transient phenomena that could hint at alien activity. Missions to Europa and Enceladus, moons of Jupiter and Saturn respectively, promise to probe subsurface oceans where life might thrive in the absence of sunlight. These endeavors, born of the same curiosity that drove Fermi to ask his question, are but the first notes in a symphony of discovery yet to be composed. Yet, for all our technological prowess, the greatest challenge remains within. The Fermi Paradox compels us not only to explore the cosmos, but to examine our own trajectory. Will we overcome the existential risks that loom over us, or will our brilliance be extinguished by our own recklessness? The answer to this question may determine whether our species ever joins the ranks of interstellar civilizations. In this sense, the paradox is both a warning and a promise. A warning that the road ahead is fraught with peril, and a promise that the pursuit of knowledge can illuminate the path forward. As Carl Sagan once wrote, "Somewhere, something incredible is waiting to be known. The universe's silence is not a void, but an invitation, an open door to the infinite." In embracing the unknown, we honor the legacy of those who dared to dream and the generations yet to come who will carry the torch. The Fermi Paradox, in all its mystery, is a reminder that the journey is as vital as the destination. For in the act of reaching outward, we also reach inward, discovering not just the secrets of the cosmos, but the depths of our own potential. The stars await, and so with eyes lifted to the heavens and hearts alight with wonder, we press on,